Hello, one and all. Back to Code Weaver Writes Code. And it looks like my audio is working, so I'm going to go straight on into the stream. So, yeah, we're going to do some more coding today. We are going to do it, again, mostly in Rust, because I'm learning Rust. Of course, I know several other languages, so I'm writing code in those too, in some cases just as comparison. Let's go straight on into the coding screen. Less babble, more action. So, and arguably not the thing I actually wanted to show right away. What I wanted to show was not that, but this, which is the description, which I'm not going to read out verbatim, but the short answer is, when I was doing an Advent of Code puzzle, which you can see on the right-hand side, I noticed that the implementation of part of the sum to n little puzzle bit of code, which is not terribly difficult to write, the sort of optimal solution I was going for bore a lot of resemblance to the way merge sort does its merging, which is that it consumes two different lists, or the same list and itself reversed, which was my sort of solution to the puzzle, but at different rates, emitting a resulting element into the target list according to some set of rules. And of course, there is an abstract, abstract higher order function called zip, which is in a lot of languages, transform in C++. And all it does is it takes two lists and it zips them together. Now, the classic zip zips them into a single list of tuples, and it consumes the two lists at even rates. Zip with uses some sort of predicate function, not a predicate, it's not a true or false thing. It's a combining function which combines them in some other way, using, say, for example, addition, or passing them off to some function for fair evaluation or whatever. The merge part of merge sort and this sum to ends problem consumes the lists at different rates, and usually actually in the merge case it always outputs an element. In the sum to ends case it conditionally emits an element into the target stream, but it's always consuming one list or the other and not necessarily at the same rate. I wanted to see if I could write that higher order function to see what interesting things it taught me. And so I wrote it in a whole bunch of different languages. I was showing the Haskell one at the start of this, and I may show that again later because it's sort of pertinent to the compactness of syntax, I suppose, among other things. But actually what I want to do is I want to show the C++ version, which you saw the test cases for just a moment ago. So I no longer need the Advent of Code thing because it's really just sort of the place that I started. And I'm going to get rid of the programmer's notepad thing, and I'm going to pull open the Visual Studio thing that has my C++ code in it. And just so that I don't forget to do it, I'm going to turn on my Rust documentation. Oh, it's already there. I'm not going to need that right away, but so let's take a look at this. My test cases involve having two vectors, templated list types in C#. I don't know why I didn't just call it a vector, but whatever. So here I am outputting the lists. I've got some overloaded OStream stuff to do this. In case you're wondering how that works, this won't work out of the box, but that's okay. It's not important. And so what I do is I zip it up using a sort of classic zip operation that only uses transforms. Let's go and quickly take a look at this. Go to definition. So yeah, all this does is call zip with, and it calls zip with a lambda, which just zips it up in a tuple. So it's solving zip with. And here's zip with, and it only operates on. Actually, this one I did operate on everything that had a standard container type in C++. This will work on lists and vectors, and I did some type wizardry here to make that happen. But ignore all that type stuff up there. None of this really matters all that much. It's this bit that's important. And all this does is it uses the transform function from C++ to do the work. So this is not very interesting from a... I just fobbed the problem off on transform, and I could have written this myself. But zip with wasn't what I was intending on writing. It was this funky merge zip with. But I decided to show what you could do with C++. Now, the reason I have to do two of these is because transform doesn't stop processing on the shorter list, which I find a bit of a shame, which means that in order to have the sort of classic zip that can take, well, I don't know if it's classic, but a lot of implementations of zip, when you zip two lists of different lengths, it stops when you run out of lists on one of them, or run out of elements in one of them. And transform does not. It assumes that the left-hand list is the shorter one, or at least not the longer one. And so I had to do a size test first, and then I just rearranged the order of the parameters in order to get both mechanisms to work. Yeah. And of course, what I do here is, in order to generate a new list out of an old one on the fly, I use the back inserter iterator, which is an iterator that sort of populates as you go. Yeah, so that's how that's implemented. Now, of course, going back to the test cases here, the next things that I was doing here, I wanted to, all the way to the bottom, come on, faster. Go all the way to the bottom here. So I did that, and then I did my own version of zip that did not depend on the C++ version. So let's go take a look at that. And again, I fob it off in the version that is zip width. But then what I do is I depend zip width on merge zip width. So this actually shows that that merge zip width, the thing that I decided to try to write, is a superset of problem solving of my zip width. Perhaps not as efficiently, although I tried to give some nod to efficiency. But it just fobs the problem off on merge zip width. And Bob's your uncle, and it solves it there. So what we're really after are the test cases that follow that. And I zipped them, left with them the parameters in opposite orders in case the order of which one is the longer list actually mattered, and it doesn't in either case. Just being safe. And so the two things that are important here are actually this one here where I do a merge, and this one here where I do that sums to n call that is part of the solution of the advent thing. I skipped the final step in the advent thing where I produce the product of the two values I found, because that's not really relevant to the problem solving here. So this basically gets out a container which is the set of all of the solutions to this. I don't just stop at the first, I just get all of them. Right. I also do a dot product in here because doing a dot product with a zip is a perfectly reasonable thing to be able to do, and I just wanted to show that I could do it with my own version of zip, just as a test case. So what we're really after is the merge and the sums to 2020. So in C++, let's quickly go and take a look at what these functions look like. So the idea with the merge, actually we should go all the way up to the merge zip width. This is the actual solution to the problem. Well, no, not that. That's some boilerplate helpful code. Here we go. These are the actions that we can take on the list every time when we're processing two lists. We want to decide whether or not we're going to advance the left or advance the right lists. And we can either step both of them ahead, we can step the left ahead, the right ahead, or we can call an early halt to everything. So this is just a way to sort of early terminate if we care to. The merge zip width takes a couple of parameters that are useful. First of all, the two lists, which are here at the tail end in this version. And I do operations on entire lists because I suppose the real reason I did that is because I wanted it to be similar to when I was doing Haskell, where I was just passing in an entire list on the left and the right. And because lists, the list mechanism is its own iterator mechanism effectively in Haskell, for all intents and purposes, this seemed like a sensible thing to do. I could have probably written the C++ version to just take iterators. But you know what? Proof left is an exercise to the reader if you want to implement a version of it that does it that way. I'm not going to convert this one because it's not worth my time. C++ and is also going to be strict in the sense that it's going to produce all these elements at once. The advantage to, I think, all of the other implementations is that the lists themselves are lazy. That is, they're not evaluated. The later parts of the list aren't evaluated until the early parts are consumed. I guess you could say they're not produced until they're needed. But that being because of the iterator mechanisms or the list mechanism in Haskell. But C++ in this case is going to produce all the elements at once. C++ ranges should change that. C++ 20 ranges. I did not implement it with those. That I will probably do in a future video. But in any case, I just took in two vectors wholesale, by reference here, cost reference, because I'm not modifying the originals. I also took in a function that combines two elements when I have elements from both lists. When this is the normal mode of operation. Oh, can you explain why you used a template for this function? Yes, I can totally do that. I will answer that immediately after finishing where I was going with this. So I'd have a function being passed in order to say what I want to do when I have elements from both lists. And I also have two separate functions on what happens if I have leftover elements in the list that doesn't get consumed first. There might be a leftover, right? Because I might do all my left-hand side list first, because none of the right-hand side ones contribute, or that just happens to be the way I'm combining into this merged list. I may end up with leftovers. So these handle the leftovers, but they still ultimately have to produce emit the same kind of result into the stream. And those functions, too, can emit a Boolean as part of the return value that say whether or not to just halt things early. So the way this basically works is I just have a big old loop here that as long as I have elements in one list or the other, I can do work. Actually, the C++ one, I have the situation in the C++ one where I'm not using continuations to return a value early, like in C#. So I'm going to be doing this as a batch, and I also don't have the ability to return it early in the way Haskell does it, where I can defer the processing of the tail of the list because of the way lists are constructed, because everything's lazily evaluated. Because of that, I actually have, since I know I'm doing it all in one batch, I can actually do the while loop that handles the double, the two lists have values in them case first, and then the two almost identical loops that process the tails on the list second. And here are the cases for what I do in terms of the advancement. And I'll walk through this in more detail later. So, Silly Queen X asks, could you explain why did you use templates for this function? Okay, so for a couple of reasons. And I kind of overdid it on actually, this one is only the vector. I did not do this one on all containers. I have some test code for that up here, not test code. I have another way to try to make it work on all containers up there, but I didn't want to obscure the issue. So this is only working on vectors. The reason I did this as a template is this. One, I wanted it to be abstract on the types of the values that were in each list. So when I'm doing a merge between two lists, if it's a classic merge, if it's just merging for like merge sort, they are going to be the same kind of value. But the merge zip width could just as easily do all of the operations of a zip, an ordinary zip or an ordinary zip width, where I'm building tuples. Let's say I'm using merge zip width to build tuples out of two lists, in which case the left and the right-hand side elements don't even have to be the same. And I don't want to even know what those types are. I don't care. I would like it to work for any kinds of types in either list. And if you want to take a look, for example, let's take a quick look back at my simple zip implementation. Not there. Here it is. No, that one just fobs off on merge zip width. Where's the one that uses... hang on a second. Come on, brain. Well, we'll just go back down to here and have it find out for me because I don't remember where it happened. This zip version. Go to definition. Doink. Here, zip width zip fobs off on zip width with a lambda to do the zipping in a tuple. And zip width does it all templated as well for the same reason when I'm zipping two lists. I do not want to know what the element, the types of the elements that are contained are. It's not really relevant to my process for the most part. Now, C++ uses duck typing for a large amount of its generics, which basically means whatever thing I do to a templated type, be it merging it in a tuple or trying to do addition on it or whatever, it doesn't decide as to whether or not it can do it until after it does the substitution of the types of the elements into the expressions. If I do a zip, the dot product, for example, let's just go to the dot product. The dot product implementation I have here, the combining function is to return x and y. Well, for two arbitrary kinds of elements, I can't actually demonstrate beforehand that the types of x and y are even going to be able to have addition performed on them. So C++ lets me get away with this because it defers deciding as to whether or not this is even valid until after it's already done the substitution. You're welcome, Silly Queenex. I hope that sufficiently answered your question. I can't do this in Rust because Rust requires me to identify up front in the description of what the containers are and what they contain to provide an annotation that says I'm allowed to do addition on these things. So I can get away with this much more easily in C++ than I can in Rust. Now, what that means, though, is not necessarily that C++ is less type safe as such. If there is a function which can be performed on the two items, then it will either pass or fail. But it'll pass or fail at this point, rather than at the call site looking at the at just the signature of the thing being called. The type safetiness person in me likes the way Rust does it. The getting stuff done occasionally makes me like the C++ version more. But I do like my type safety. If this weren't type safe, then I would be entirely not with it. And there will probably be lots of people who will make the perfectly valid argument that if you can get this far and perform this operation and it compiles, it doesn't necessarily mean it's sensible to do so. But if I tried to add, for example, an employee and a float, a structure and a float that has no addition operator, it will fail to compile. So, right. Let's move on from that because that's not the interesting thing for the sake of the problem today. This is the C++ version, and I wanted to show it because I've been showing the Haskell version at the beginning of all of this, but the Rust stuff, even though the type system is very Haskell-like in many, many ways, Rust is meant to argue zero-cost abstractions and high performance and all the like, and that would be where my C++ version, I think, is going to possibly come out the winner. The other difference between this and the Rust, because I'm not using C++, C++20 ranges, which have iterators be a self-contained entity that can walk through a collection. In Rust, an iterator can walk through a collection with just one value being an iterator, which knows when it starts and stops. Classic iterators in C++ require pairs. You require a beginning and an ending iterator that you do comparisons against so that you know when to stop. And the problem with this is it's not very composable. You can't build these iterator pairs out of other iterator pairs, at least not really, really sensibly. The one difference that you'll see is that when I go to call the function that does the combining, among the things that I do is I pass in the two elements under consideration. I also, just for, in case it's valuable to the caller, pass in the iterators that are involved. But in this case, I have to pass off, actually, two pairs of iterators. And this could be made a lot cleaner if I could get out from under having to do this. I'd like to only pass in a single iterator to show the rest of the list. And the reason I did this is for look ahead. If you want to look ahead in the list to make some determination on what to do. We could probably make this more efficient by getting rid of that. Eventually. That being said, we're not interested in the C++ version except to give it a run and make sure that it does run. And I may have to, I wonder if I can show that window without causing major grief. That would be the... what is the window called? Debug console. All right, let's see if we can do this. VS Debug console. yes, I can show it, but it's way behind everything. So there we go. That's what we're going to try to get out of the Rust code. So, and what you can see here is just, so at the top here you can see, let's see if I can scroll back, the two vectors outputted individually, the zip of the two using the C++ transform version of the zip that I showed you earlier. And that's both the left-hand and right-hand versions of it, basically, with the two parameters swapped. And all you can see is it's building up tuples. You can see that it's doing 5, 0, 7, 1, 8, 2, and so on, which is just the pairings in tuple form. And, of course, the reverses of that. Then, of course, you see the two zips showing the using the version of this that ultimately ends up fobbing all of its behavior off on my merge zip function. Exactly the same output. At least I think it's exactly the same output. I'm pretty sure it is. And then finally, we have the merge, which merges the two lists together, and we have the dot product, which of the two vectors, which only goes up until as long as each one of them has a pair. Each one of the lists has elements, and that sums to 20 operation, a sum to n operation, which says among the two test lists, which are sadly only visible in code. So let me scroll to that. I didn't output those independently. There they are in this list, which comes right from the advent of code puzzle. Find me two values in that list that add to 2020, any two values. And you can see that it quite clearly solves that as well. And all of these last five results here all come from the new function. So it works in C++, does what it says in the tin, just like the Haskell version. And we're going to get rid of that, because we're not going to look at the C++ anymore. At least not for now. Let us pull open VS Code. Well, we're back in Rustville. Finally, we're back in Rustville. We also don't need the advent of code window, which you can't see anyway, so I'm going to close that. So, I did a little bit of coding off stream, and that was a lot of fun. I did not have access to the ability to do OBS, and I wanted to try to tease out some of the problems I was having. And if you recall from the last stream, for those of you who are in the last stream, or watching the last video, I was toying around with the problem of trying to build my personal zip function off of my personal zip width function, which then was built off of my personal merge zip width function. Like, I wanted to daisy chain these behaviors together. And the problem I was having is a complication in the type system, which I will be going into after I show you the real cool thing that's happened. So, here's what we're going to do. We're going to do a little cleanup here. I've got some Haskell code buried in here, so I was doing a comparison. And I'm going to get rid of... I don't really want to get rid of any of this code because that could be problematic. But here's my test cases, and you can see that they are more or less what you saw in the C++ version. In fact, almost identically. In the last stream, these were all .iters, and the problem with that is it was generating references, which didn't really matter for the kinds of code that I was doing, but I wanted to make sure that I was operating purely on values because I didn't want to deal with processing references yet. I did, however, also have to change this from VXS to alone to this in order for this into iter not to consume the entire vector in the process of doing this. I don't know if there's a better way to express this syntax, if I'm honest, but what this does is it says call the into iter version that takes one of these vectors by borrowed reference because I don't want it consumed. And Rust is really big about consuming values that are not handled by reference. Only one thing can own data. It doesn't matter whether it's living on the heap or living on the stack. Only one thing can own data, and much of Rust's really interesting power, I think, comes from that, aside from absorbing a really strong type system. But this stymied me because well, you know what? I'm going to first prove that this actually runs. Yes, I got this working. So I'm not actually going to be walking through developing the merge zip width. I actually got it working. So we're going to fight with other problems today, but I wanted to show what I had come up with. And so hitting the run button and letting it, I really do have to tell my virus checker not to go scanning the executables I'm generating, but I am rambling, but check this action out. So here we go. I'm going to make the terminal window a little bit bigger here. So here we go. We have the two original lists. We have the zips that are done not using... in the C++ version, I wrote one using transform, just to make it a little cleaner. But in this case, I actually used Rust's zip function to do these two. Then I used mine. Did I output XS and YS again? Hang on a second. That seems odd. Oh, did I accidentally run this twice? I might have run this twice. Let's do a CLS and rerun this thing. There we go. The second pair here are the zips that are done using my own zip. This is doing the merge of the two values, and I think that's correct too. And the xs.ys is producing the right dot product. And here are the pair values from that list, which add to 2020. So it does exactly what C++ says in the tin. Here's the fly in the ointment. So I'm going to go into how these are implemented in a second, but the reason why this is slightly unsatisfying is because when I did my own personal zip operation, I could not fob off the result. Actually, I could fob it off on my zip, but only if I said that the thing that I was zipping with was a pure function pointer and not a generic object able to contain a lambda that happened to follow the signature. And there are reasons for that, and that's arguably going to be one of the things that we're going to talk about going forward is ways to get around this or what my better implementation should be. I want this to take an arbitrary lambda, and it can't. It looks like it does. But this kind of lambda is special because it's not capturing any of its internal state. And we spent a chunk of the last video looking at various interesting ways to explore being able to return. The ultimate problem ended up being not being able to return an iterator that contained. Not being able to. What was the way I had to state this? In zip with, I couldn't return an iterator that contained an unboxed closure, the function, such that my zip could then in turn return it as well. And that was a problem. What that means is zip and my zip both have to effectively, they have to be built without fobbing their responsibilities off on my zip with, which I find a great shame. And I can't find a way to work around it that doesn't involve allocating something on the stack or passing around a virtual dictionary. I was trying to keep this as reasonably efficient as possible. So we're going to get to that part of it again because I think that's arguably one of the more interesting things about this little puzzle space is working on this. But I wanted to demonstrate today that ultimately the merge zip that I originally set out to do actually functions. And so I wanted to talk about actually showing how that works. Except I kind of did off in the C++ version, right? So starting right at the top here, let's take a look at this. I have this just to be able to, during testing, say, don't worry the fact I'm not using these as a sort of library code, so these aren't being used. It just means I haven't written a test case for it. But these are my actions. I can, during processing both lists, I can advance either both left, right, or halt the entire operation. The merge zip with here is the actual iterator that contains the state as this thing operates, and the corresponding code for the implementation for the iterator trait to make it iterable says that the items have to be copyable because I'm not messing around at the moment with other complicated wizardry. If you want to work with references, you can pass vectors of references in there, and the references themselves are copyable. But if you're passing any vector structures or integers or whatever, they themselves have to be copyable for this to work. And that's fine. These are the descriptions of the way the functions have to look, and you'll notice that I'm using the function trait so that in principle these can hold closures, and I can show you that in fact holds closures just fine. Here we go. Here's my big fn next loop, and this one is a little bit unlike the C++ version you saw in that it is just one loop and not 3 loops one after another. The reason for this is, like C#, I can return a value sort of from, well, I'm implicitly doing this in a sort of a continuation passing style in the sense that next gets called for each element. So I can do whatever I want in here, but ultimately I have to return out of the entire function, but it is operated in a stateful way, which is a little bit like what happens when you yield return a value from the middle of a C# loop and then allow you to continue where you left off. In this case, I have to exit the function entirely to get that same effect. But in a sense, the principle is still the same. I am not processing the entire list all at once in this loop. Really, all next does is say, get me the next valid element or tell me to shut down. And so that's exactly what I'm doing in this Rust iterator. And so the first thing that I have to match against is, do I have elements in one or the other? But I don't want to consume those elements from the list as I'm doing it. In order for that to work, I have to be able to peek into these iterators. I have to be able to look ahead to see whether or not there are elements to process. And unfortunately, if I call next here, in order to iterate, in order for my iterator to iterate the other iterators, I will advance them when I may not want to, because I may not be advancing one or the others of these. So I do the peek first, and if I have no elements in either one of them, I'm just done. This is literally the way I stop operating on the lists. And the break none syntax works when you're inside a loop to say that the value of the loop as a whole is the value of the that comes after the break here. One of Rust's interesting things is, although it has an imperative syntax when you need it, like it's C-like, the C cousin-like syntax when you need statements, it is very much an expression-oriented language in the sense that if you have a function that produces a value, all you really have to do is state what that value is as an expression. You can do that prefixed with a number of statements to do imperative style sort of stateful computations or whatever, but ultimately at the end you don't necessarily need to do a return value like you do in C++. You simply state what the value is. And you can see this right here. There is no return statement after this loop. The loop is the value. The thing that I say break on is the value. So I always look for blocks of code and think, how can I do this in a value, an expression-oriented way rather than a statement-oriented way? And actually, there is very little code in here that is in fact imperative. I simply don't need it. So the value of the loop, there is actually a value in this match, but I ignore it. And the reason for that is because I'm actually using the breaking out of the entire loop to produce a value for the loop. So although matches produce a value, the value of all of these operations is basically unit, void in other languages. So match has a value that's a void, but I'm ignoring it because I'm not doing a let. I'm not binding anything. Let void. I could do this, but then what's the point? Because I'm not actually using it. I'm actually breaking out of the entire loop, not just the match, with a value. So that's the technique I've chosen here. Hey, Rustaceans, if you come by this this video, come see and tell me whether or not I'm doing this in a silly way. I think this worked out pretty well. Anyway, so there's the ultimate breakout case. Here is the case where, okay, so I am handling the cases where I have some values, at least one value in the left-hand list, but the right-hand one has become exhausted. And the same thing happens down here. The left-hand one is exhausted, but the right-hand list has some value that I might be able to operate on. In either case, I call the appropriate function, pulling out the value that I know is there and advancing the list and unwrapping it at the same time because I know it's there. This can't actually fail. And then it then does an additional test. Matching on that, each of the values returned from this kind of function says, do I continue the list? And if I do continue the list, what is the value I want to emit into the stream? Well, I ignore the value that's in here. I ignore the value that's in here if I'm told to halt the stream. There's a number of ways I could have chosen to do this. The fact that I have this returning a pair instead of building up something more intelligible in terms of my return value, a tuple, I guess. It's just the way I chose to do it. I probably could have done that better. I probably could have bound. We'll discuss why I made this design decision later, but the basic idea is in the one parameter version where I only have one value from one stream, I still need to produce an R if I can, and if I can, and I'm not halting the loop prematurely, I just emit that value, right? So whatever value I get back to the function, that's what I put in. Same thing on the Y side. I use a different function because it could be a different type, but I do the same thing. I unwrap the value after pushing the stream ahead, and if I say don't continue processing this merge zip, then I just return nothing, and otherwise I return something. I return specifically the value that was wrapped up in there. The case where I have two values, because I have one from each list, is going to call the appropriate two-parameter function. It's again going to get back an R, but I have to do this slightly differently here because I may want to advance one or the other or both, so I can't do the next and unwrap trick buried in here. But what I can do is get the value back and ask the question, all right, what action do I want to take? And in the process, extract the R value that I know is there. Because here's the trick. If I... there's actually a bug in this code, and I'll go back and describe it in a second that I've just noticed, I think. What I say is, if I can match that I want to advance both and I have a value, then I advance the two and I emit the value. If I have only the left, I advance only the left and I emit the value. If I want to advance the right and I have a value, then I emit the value. In all other cases, either because I've said halt, or I have or I can't match against some, then I break out early. But this is not a complete list. I'm noticing I'm missing something here in all of these cases. And that's the case where I said I have a value, but I did not manage to match against this. That means that I have a value that I'm trying to filter out. Isn't this interesting? Isn't this interesting? What happens if I do that? In that case, I would say break none, and I would halt the list entirely. I think I have a bug in here because I have allowed the option of the function saying, yes, please continue processing, but the value that I have, that I want to return, don't include it in the list, and that allows you to filter out elements. I'm kind of wondering how my sum to ends thing is actually working now, actually, because I think what's going to happen is it could conceivably halt early before it finishes the filter. We may still have some code to write here. All right, that's a thing. Yay! And the same thing goes up here. It goes for up here, actually. There's a situation here where I want to say that we can get a I want to continue, but not have an element to actually emit into the list. And you see, there's where I happen to handle the case here. In the case here, if I were false and anything, then I stop immediately. But if it's true and I get a value, then I emit it. Otherwise, I do nothing. So I've handled it correctly in these two cases. I have not handled it correctly in this case. So isn't that interesting? Great. We've now got our new problem space. I've got to make sure that I handle the case where I can correctly filter out elements that are not correct. So what happens... Let's take a look at the one case where I actually need the filtering, because the merge doesn't. It always emits a value. Every time it compares two values in the merge list, it always emits one out to the outside. In fact, let's go and take a look at that very briefly. Here's the merge. The operations here are thus. If you recall, I have to provide the left hand right list, the left hand of the list, the right hand of the list, a function that combines the values together or chooses what to emit based on two values. It's not actually combining, it's actually just choosing. And in this case, the situations where we have only one element from one of the lists because the other list is exhausted, we just output that value. So it literally copies the tails of the lists in place, which is exactly what you expect merge to do. Perfectly sensible, works just fine, does what it says in the tin. Sums to n is a little bit more complicated. Now, the first part of this is actually is more setup, and the basic idea here is I need to sort the incoming list because the inputs are not sorted initially. I then construct a copy of the list that is reversed, and then I process those two lists inside of this particular application of merge zipwith. And I did this rather than something more specific, like walking forward through the list in one direction and backward through the list, using another iterator, because I wanted to use my merge zip. My point is, could I solve it this way? And it's still, an ON operation, but it does require those list copies. So one of which you'd have to do probably, well, you wouldn't have to copy it if you did the sort by way of an in-place sort, but whatever. Here we go. Here's how this works. So the sorted version and its reverse are the two lists that are being passed in here. When I do that, basically, what I do is I have to match. So I have the two parameters coming in, the two values coming in. I have to pass try to match against a comparison between the y and the x components on this. Right. If the and this is just to say whether or not x and y are actually equal or crossing over, because x is going to be increasing as we iterate through this, y is going to be decreasing, and if they ever cross over, then all I'm doing is pairing a larger value with a smaller value, with the larger being on the left, and at that point I'm just introducing duplicate solutions. So this is my early out case right here. So in that case I just halt and don't output any sort of value. What I want to do here, though, is in every other case, it means that I'm not in my halting case. What I want to do is I want to compare the target value, which is 2020 in this case, that's from here. I want to compare that against the x and y values. And the ampersand here is to actually pass in a reference, because partial comparison expects a reference. I know there's going to be a solution to this, so I just arbitrarily unwrap it. Given this, actually this could fail on floats, for example, if one of them were in NAND, but then I'd want the thing to halt anyway, so I'm not worried about that. I'm perfectly happy with it crashing if it gets fed in NAND for the sake of this demonstration. So if the two are equal, then I've actually found one of my solutions, and literally I just output a tuple that contains the result. If the ordering is less, that means that I'm too low. And what I want to do is I want to come up with a new pair to add that increases the value. And if I advance x, that's going to make it bigger. But if I advance y, it's going to make it smaller. I don't want to make it smaller. I want to make it bigger. So I advance the left-hand side. But I also output that I do not have something to emit into the stream at this point. And in the case where it's greater, the exact opposite is true. I want to advance the right. And I want to say there is no value here. Now you could argue quite sensibly that this merge zip with I've invented shouldn't be doing filtering at the same time, and that's perfectly plausible as a solution. What I would say to that is, I actually agree. I should make this more pure of a function by removing that functionality for the efficiency of programs that simply don't need to do a filter. So what that would mean is there are going to be, if I did that though, what I would have to do is I would have to omit not just a tuple as a result. That was the sort of final output value. I'd have to output for this particular solution an optional value that said whether or not I had an entry or not, because I want this to still operate as if it were a stream, and or it was an iterator. So what that would do is the output list would not be a list of tuples of the results. It would be a list of maybe I have a tuple and maybe I don't, and then I would have to go and filter them after the fact. Now that would put the onus on the filtering on the caller, and that's a sensible constraint maybe for the sake of some performance. It would mean that operating the standard merge algorithm would actually be more efficient because it wouldn't be doing all these filtering checks because it wouldn't have to. But this is the way I did it. So my merge zip does filtering on the elements if you output a none. Yay. Here's the problem then that I spotted earlier on, possibly. And I want to make sure I didn't, it may or may not be a bug, but the basic idea is that if I output a none, if I'm in any of these cases where I'm outputting a potential none, but where I'm not halting, is it properly doing the filtering? So I'm going to see if I can put some breakpoints here. I have not used the debugger very much in Rust using VS Code, so this will be an interesting experience. I want to see what happens to my test cases and whether or not I implemented this correctly or I just got lucky. Because this has to be right. It can't only work for my select inputs. That would be ridiculous. So, we're going to do a little debugging. Because we're not done with this until I'm satisfied that it's actually doing the thing it needs to do. I'm going to comment out, though, all of this junk. Because I don't need to see any of this. And in fact, I can comment all of this out, because we're operating on this limited vec here. So just build that, make sure it still builds. I don't like being accidentally right. That's just not cool. Function never used dot. Oh, right, because we have this warn dead code problem. I actually like the fact that it warns about dead code. Like I would hate to... I often find that in my projects, as time goes on, I end up with more and more cruft code in some of my modules. So we're just going to blanket allow dead code in the whole thing. But when you're doing tests like this, it is slightly annoying that it shows up as an error. Except that's not going to work, is it? It's that allow dead code is not universal. I have to do it on each of the... Really? I have to do it on each of the functions? Is that what you're going to make me do? Yeah, I think it is. That is kind of annoying. But that's okay. I will live with that. So it's upset at me because of this. No, I'm actually using the sum stand code. Here we go. All right. Hit the magic. Please debug this for me. All right, so it didn't break point. This is a good thing to learn. I haven't done debugging on this very much yet, but it did not break point on these two things. I guess because it doesn't consider it code, and because actually that's only on the result. Well, okay, let's find out what happens. We're going to take a step. And can we, do we have values in each of the lists? Well, we're going to find out because I don't know how to do. There's an iterator. Its capacity is 6, but it's probably not going to tell me more details. What happens if I open this? A pointer to this, which points to 366. But it's going to be really, and then 299. It's not going to, I don't know how to dig into what these mean. Because I'm not used to debugging Rust yet. That's basically it. I have, like, I can look through a C++ vector in Visual Studio and kind of figure out how the memory map is worked out, but I can't do it on this because I'm just too new. But I can step through this, and I know I have 2 values, so it should actually eventually pop all the way out to here, where it says we have 2 values, and it's trying to do a match on the result. That's the call stack. There's some watch values. Here's my locals. Look at that. We have the 2 values X and Y. Sweet. And yes. And they are references because that is what gets bound here, because the sum is holding on to a reference because of the fact that I use next. I think that's the way that's working. That's why I had to dereference these, because they were references. But then Rust automatically dereferences references under certain contexts and not others, which is a little weird to me, but that's all right. In any case, we have both of them. And we have some R value that has come back. What is R in this case? It is 299 and 1721. Let's just run until the next loop, and the next loop still has 2 values. And it has gone into the greater clause, so this is what is actually tested. And this is because the sum of these is too high. So actually what we're going to do is we're going to advance the right-hand side. And that takes us into past all of these clauses, and it does a break none. So I have accidentally solved this problem and not actually solved this problem, because this should not be stopping the entire stream search. What it should be doing is saying that if I got an action to do a left or a right, but there's no value, or both for that matter, if it says to advance both and it got no value, then I should be advancing it, but doing but then doing no other code so that the loop keeps operating. This is actually going to stop the program entirely, which is which is not the right answer, because it's not going to find all solutions. I actually need to add more cases. So how do I want to do this? I need versions of these where I know what to do in terms of the advancement, but this is a none. So that means another 3 cases. Or in each of these, instead of matching against some R, I could match against an optional R, like just call it OR, I guess, and then break it apart in here and conditionally do something. That may or may not be good code duplication, I'm not sure. Let's see, let's try this. Let's try fixing this, where I say I'm actually going to capture the entire optional value here, because I want the advancement to be the same. But what I'm going to do here is say if, I'm going to do an if let R equal sum of R, then do the break. Now I could do this with a match as well, but because I'm doing this as a statement and there's only one thing I'm testing again, this is what I want to, I think this is what I want to do. Now, but that's interesting, isn't it? Because all I'm doing is unwrapping a sum r and then returning sum r. Oh, sorry, it's sum or. So, no, hang on. Let I've done this exactly backwards because I'm just not awake. I want to actually do that. But this is silly because I'm unwrapping it just to rewrap it. And in this case, what I really want to do is just break R. Or sorry, break OR. The optional version of R. Look at that. Don't unwrap it just to rewrap it. What's the point? Yeah. Yeah, this is actually the right answer, because then that actually removes that actually makes it so that I don't have to return all of the cases here. Or I don't have to add the 3 additional cases here. So this does make me wonder, because the solution is right at the front of the list, which is a silly test case. The thing is, I wonder if my C++ version has this same bug. I don't think so, but I don't actually know for sure now that I come to think about it. Should I go back and check that? We are going to go back and check that, but not here. So, but in order to make sure that this doesn't happen again, we are going to make a change to all of our test cases where we don't have the resulting values at the maximum and minimum entries in the list that are possible. So we are going to have to, at least one of the things we're going to have to do is add a pair in here that adds up to the result that is not just accidentally at the top of the list. That's probably the easiest way to do this. So we are going to break with the puzzle as we have given it, because, I mean, it's just that the minimum and maximum just happen to magically work out. So 366, so 2020 minus 366. I can't do that in my head because my brain's too fuzzy. So 2020 minus 366 is 1654. So if we add a... if we add a 16, do we want it to be, actually, there's an interesting problem. We actually want it to be kind of in the middle of both lists, I think is what I really want to do. So why don't we do... 10, I can't do 10, 10, I could do 10, 10, and 10, 10. That's an interesting test case, actually, but just for the sake of argument, let's do 1019 and 1021. Now those are going to get sorted into the middle of the list, so by the time it does the iteration, it's not just going to be picking those up at one end. But if we add those two things together, I can't do math to save my life. That's actually going to be... all together now. Right. So now we should get 2 answers out of this, because those last 2 should actually come up. But they're actually going to get processed in the middle of the loop. They won't get processed at the beginning because of the sorting. Time to do a run, which is going to involve a build, which is... actually, I don't know if it actually did a build. Let's just double check that it did a build, please. All right. Hit the old run button. So, first two values, 17, 21, and... Okay. We're going to go into the case where we have both values. There we go. 299 and 721. And that is, in fact, one of the solutions. And we know that that's going to happen. And we're just going to return the value in question. Then the next time through the loop, we're going to get that it's that the value, the sum of x and y, are too big. And so we're going to advance the right, which is then going to advance the right. But then it's going to say, oh, actually, no, this is wrong, because OR is going to say none. That's why we wanted to do this, is that we didn't want to actually do the break at all. This is actually not solved a darn thing. It's just going to terminate immediately. Okay. That's why we want to do the if flat. So sum R equals OR in, and only if we got a sum out do we want to output this. Because in this case, a none from our function doesn't mean terminate. It just means I have no value. In that case, we, break... why are you complaining? Brain is not functioning. Unused variable R. Oh, because all I'm doing is a test to see whether or not a pattern matches. But then we can return the original OR. There we go. Now what'll happen is if it doesn't match because the function returned a none, it will do nothing. But then it also won't break out of the loop. And having already advanced the iterators, it will continue on its merry way doing the right thing. All right, test case, we're going to see if the F5 does actually do a compile. Huzzah! All right, so the first one we know does what it says on the tin and emits a result. Don't care about that case. Next case, it goes and does the greater operation, which then steps us into this case, but it says, do we match? We don't, but then we just continue back up at the top of the loop. Are there still elements? Well, yes, there are, and in this case, it's still greater. 366, that would be 13. Oh, look at this. I have made a mistake here because of the order in which I'm doing the comparison. I'm saying, what is t's relationship to this? I'm saying t is greater. If t is greater, which it is, that means x and y are too small, so I should actually be advancing the left and not the right. And the reason I did it in this order is because I wanted the ampersand business on this inside this function call for whatever reason. The thing that I could reverse the order of all of this, but I think what I'm going to do is this followed by t. Expected ampersand t found type parameter t. Okay. I gotta think this through here. This one needed to be an ampersand because it expects it to be. Because it expects it to be a reference. Is this already a reference? Does the add actually effectively produce a reference? See, I'm looking at this and I'm not convinced as to why this is working. If this is passing in, so partial comparison takes both in as a reference. Or maybe... I'm not 100% convinced why I kind of get why t being a value. Doesn't need the ampersand in front of it because that's a value and that's a value. So the addition of the two should be done by copy. Not 100% sure. It builds and I don't know why, and that really bugs me. Both have to be references and it produces an ordering. Why is this considered a reference, but wasn't considered a reference when it was in the parameter call? Is this because of an auto dereferencing thing when we're calling a method? This is one of the things that drives me a little nuts about Rust. In some cases, they decide to save syntax, and in others, they don't. When you use the dot operator, it can automatically unwrap one level of reference out of, I think, one level of reference out of its the thing that's on the left-hand side. I think that's what's going on here. In any case, the function has compiled. So the basic thing here is I've just reversed this comparison, and this happens to read more like the logic that's in my head. If the sum is greater than our target, then we do something. Otherwise, we do something else, etc. I could have reversed these cases, but instead I decided to reverse the comparison. So I had to give it a run. Eventually. Here we go. So, first case you don't care about. Second case is where this starts to get more interesting. See, now it's coming up less, which is what we expected because we reversed the idea of the comparison. So here's the problem. 366 and 1456. That is 17, 18, 11, 18, 22. It's too low. And in order to make the sum bigger, and given that we know the x's are not decreasing, they're increasing or staying the same. X's needs to advance. The left-hand side list needs to advance. So let's run to the top of the loop again. And now we're back in the both case, I think, because I should have put the breakpoint here just to make sure I catch it at the beginning of the loop. This one said that the left had to advance, but it still had a none, so that's fine. Match. What have we got here? We're testing against 675 and 1456. So in this case, we have 2131. I should actually have, I mean, you could argue, why do I not have a temporary variable here? And the reason why is I'm trying to do this in a reasonably value-oriented way for the most part. And because I'm not reusing this x plus y anywhere else, there's no harm in putting it here. What I could have done is a let before this move, I suppose. No, because it needs to be part of this. So in order to make it work, I would have to introduce the variable, a variable s for sum, let's say, as for before the match, but basically as part of this move lambda. Yeah. All right. So it's hang on. It's saying it's greater, and so it has to advance to the right. Why is that? That is, we're going for because it's 21 something something. It's bigger than 2020. So we actually have to advance to the left. So similar problem. We step through this and when we get back in here, we're now saying that the sum is actually less. So this is 1686, and that is in fact less than 2020. So I'm going to advance to the left. This case, it's less again, and actually I'm going to put a break here just in case we catch another example, which we will eventually. 979 and 1011 give 1980, 1990, which is again too low, so we advance to the left. Oh, and take a look at that. We have found our next test case, which is 1009 and 1011, which in this case we do both because we have found the pair in question. And this is an interesting problem right here, because if I had duplicate values in the list, I would advance past both of them. And that may not be fair, because if I had a duplicate, say, 1009 in the works, but not a duplicate 1011, I would step past the 1009 I needed to match up. But this is not a problem with merge zip. This is a problem with the implementation of the sum to n mechanism, because I could just as easily say, well, if you find a match, just advance one of them. So my implementation actually makes the assumption that there are no duplicate values in the list. But you know what? That I'm not going to alter, because my solutions and all of my code, my implementation of the sums to n using merge zip and all the different versions of my code all behave that way. So I'm going to say that that's the new definition, because deal with it. There are no duplicates in the list, because none of that is going to change whether or not merge zip works. I would just have to write a slightly different version of the sums to n problem. So having done this, go right back into the top here, and we're going to pull out values. But the problem is that we have hit the case, actually, where we've gotten nones out of both elements of the list, and so we are just, in fact, completely done. We didn't even end up in either of these cases, because we just happened to meet in the middle right when there was a final pair to match. So, and there we go, the two answers that we were looking for. The original, which accidentally happened to be at the start of our list, giving us false sense of security as to the efficacy of the code. Make sure to test more test cases, people. And then the second one that we introduced to make sure we were iterating through the loop fairly. Right. Off to the C++ version of this to see if we screwed that up too. Or if I did, because I didn't do that on stream, and anyway, none of you had any input on it. So let's quickly close out the VS Code window and the Visual Studio. Why is Visual Studio not popping up? Did I not leave that open? I guess I did not. Let's reopen it. All right, there's the C++ version. All right, so we are going to do exactly the same thing as we did in the Visual Studio version, which is to add those extra two test cases and see what happens, because if I have a bug here, I want to know about it. That's fine. Sorry, I'm in a window you can't see, but now you can, I hope. So there is the result of the change to the C++ code. And now we're just going to give it a grand old run. And we are going to go over onto, oh, good. The window actually showed up where it was supposed to, ish. So there you go. You can actually see at the tail end of this, it actually outputs both results. So I did not screw it up, at least not in that same fashion on the C++ version. Time to pop over to the C# version, because we're going to make sure that we didn't screw this up anywhere. Let me see if I can find it. I think that's the one. Yep, okay, so add the extra two test values to that as well. Hit the magical run button. I don't know if this console is going to pop up on screen, But if not, I will try to make it so, just to verify, I will have to do a clone of, I have to do this on the fly. Add window capture, add an existing Visual Studio console, except we're going to have this one be it has given me two windows. I didn't think I had both of them open. .NET 5. No, this is not what I wanted. I wanted okay. There it is. That's the C# version. That's what it says on the tin. Actually outputs the two values, and it looks like we're happy. Right. Right then. We're going to close that one, and we are going to close. So we kind of closed both of them. I'm not sure how OBS deals with those two windows being similar types, but that's okay. We're just going to hide them anyway. Let's go to what is the best way to do this next bit. I need to show the result of the Haskell version of this. Okay. Right, close Visual Studio. Just unfortunately left a black screen. Re-enable the programmer's notepad. So I was just doing this in a PowerShell window, which I'm now going to need to All right. Documents, programming, Haskell, stack. CD, you are not seeing any of this because I forgot to turn this on as well, but give me a moment. All right. We're going to do some quick little renaming of things here so I don't get confused. So it's Visual Studio 2019 C#. Let's rename both of them because whatever, I don't care. Window capture. I'll call this Haskell shell. And that is going to be yes. I guess that worked. Don't know why I didn't have one of these pre-created, but let's take a look. So stack run. So let's just make sure that it still runs as it says on the tin beforehand. That's fine. And so we're going to go over into the Haskell code and see what happens when we add the two additional elements. So that is going to be so you can see that I just did basically I assigned sums to 2020 to be sums to and applied to 2020 and the list in question. And so, yeah, that's fine. So I need to add the 2 original values, which I need to grab from my C# code. I have to make sure all this stuff works. So there's my 2 extra values. Do a run. Grind, grind, grind. And there we go. All right, so that one didn't break either. Apparently I thought this through a little bit better on these other versions. This goes to show you when you're fighting with a new language, you get a little bit sloppy. All right. All right. So we've done that test, and now we can revert all of these windows back to showing, not Visual Studio, thank you, VS Code. There we go. Guess we don't need the programmer's notepad open either, so we're going to close that, make sure it's out of my face. Where were we? We have gotten all of this working for the cases that I was trying to test. This actually, as far as I'm concerned, this sort of addresses the issue of, can you write something fairly generic that does the operations of the kind of dual list walking where the lists are consumed at different rates and produce values as you go. And on the face of it, the merge part of merge sort and the sums to end thing don't bear a lot of resemblance. One of them only outputs some sort of end result values that match a condition. The sums to end thing. I mean, a merged part of merge sort is literally taking 2 lists and interleaving them so that they stay sorted. While every step basically outputs an individual element, and it consumes all of the elements and it produces all the elements from each of the lists without missing any. So the only thing that in principle these have in common are some, and in fact one of them does what's even more interesting is that one of them sort of fuses together the answers. The sum to n actually fuses them together into a tuple, whereas the merge sort doesn't actually fuse them together as a result of it. It actually just outputs one element or the other. The fusing of x and y is either x or y. It's no combination of the two. But at the heart of this is a mechanism whereby you are applying a function to say, given these 2 values at the start, these 2 values of these lists, tell me what to output as a result. And the other commonality of this is, in the process of doing that, just tell me how I should walk through the remainder of the list. And it turns out that in both of these cases, you can solve this using a common function that is pretty handy, kind of abstract, doesn't require you dealing with the loop part of it or a lot of the decision making, except for that which helps you decide what to do on the next values that are passed in. And obviously sums to n is a little more complicated than the merge part of it. But I mean, taking a look at the merge, it's pretty simple. And in fact, if you didn't have to apply these for the tails, the entire merge process really only comes down to that. All of the mechanisms for doing the list processing and advancement, all that is all handled by merge zipwith, just like it's happened with ordinary zipwith. Pursuit of not writing lists manually, like doing it once and then getting it out of the way. This is actually the heart of the merge operation. But I am writing this internal piece of that merge operation so that a generic machine can grind on it and just spit me out results. I actually like a lot of this sort of inside-out programming where you don't write the surrounding superstructure just to be able to write the core. You write the core, and the surrounding superstructure is common to a lot of other problems. Higher order functions, it's where it's at. Now, whether or not merge zip with is a valuable higher order function is a completely separate question. It does, the more complex you make a fundamental operation like this, often the more sort of support goo you need in order to bootstrap it. This bit doesn't count. That's just the setup for the problem. That looks complicated. And you have to think it through, and obviously I didn't completely when I first wrote it, and now I've got it fixed. Now I haven't shown an example that actually says what to do with conditional processing of these tails. I've really either accepted all of them universally or thrown them away universally. And in fact halted early. But I think that this has sort of illustrated the point. If anybody has some interesting uses I could put this particular kind of function to, please feel free to drop me a note. I see you are trying VS Code. Hi, Silent Z. Yes, I got it working well enough to be able to do my builds and to be able to run them on stream. I am so used to Visual Studio and a couple other building packages, mostly Visual Studio, that the fact that this is all plugin based and making sure that all the commands are hooked up in the right way, it wasn't too hard once I sat down and followed the instructions, but it is very plugin-y. But I got it working well enough for this. I'm not sure how I would feel about using this as my primary development environment, but if I were doing something that wasn't automatically handled by Visual Studio, actually it's not half bad. Certainly better than using an editor window in a text program and a separate window for running the thing, although I do have to still do that on the Haskell side. I'm sure there are Haskell plugins for this too, but it's not super important just yet for me to go down that road. Anyway, have you tried out Rust Analyzer extension? I have not. Okay. That's my new plugin project for the next week. I won't do it on stream right now because that's just boring plumbing paperwork, but I will give that a shot. Yeah. All right. Yeah, so Silent Z, I don't know if you've been watching the stream, but hey, we got something working here. Let's take a look. So I don't know if you've seen this. We have, finally, the exact same program running in all 4 languages that I've been futzing around with for the last little while, including a properly working Rust version of the merge iterator. I'm still, so there we go. There's our output. I got duplicates here. It actually starts here. And yeah, I ended up outputting, for example, or actually it starts here, I guess, whatever. It outputs the various pairs of zips. No, I need to rerun that. That's clearly nonsense. Oh, that's because I got the, no, that's because I did the, need to stop that. Let's, where the heck are all my breakpoints? Run without debugging, please. There we go. Yeah, so we've got the built-in zip. We've got my zip based on the merge zip with mechanism. And actually, did I fob off on that? I can't remember. This is where I'm actually using merge zip with on purpose directly to do a merge operation, to do a. Is this where I did it with the dot product? Yes, and the sums to 2020 problem, which now spits out 2 solutions just to be extra super sure that I got through all of the cases of my code that I cared about. So, yay, it actually works, and it works actually pretty well. So let me take a look very quickly at my zip solution. Basically, the primary reason it works, and the primary reason it was able to fob off its results on my zip width, is because it actually passes in or expects to pass in as its type a function pointer and not a full lambda, which is a bit of a problem because I had to I discovered in my last tests that in order to get my zip width to pass off its problem on merge zip width up here, I couldn't do it. The problem being that I was trying to return. That's my zip withable. I'm getting lost in my own code here. I could not get my zip width to fob off its problems on merge zip width because I could not return from a trait an impl iterator. And I couldn't get the appropriate type to be able to construct the merge zip width out of it. It's extremely unfortunate. I saw a spot on Twitter of somebody implementing combinations functions with const generics for the first AOC puzzle. Ooh, that could be kind of exciting. I should check that out. So the version of the version of my zip withable that I would actually prefer to implement is where I actually defer all of the behavior on my zip width off to merge zip width. I can't because of this return type, because I need to pass in this lambda that wraps around another function. But the type of this has to be equivalent to this, and it isn't. And this was the big thing at the tail end of one of my earlier streams. I cannot make this work. So actually, Silent Z, you can maybe clue me in on whether or not this is plausible. But let's say, so this is my working version of my zip width, which just handles things directly. It takes, for my zip width, it takes a function, which could be a lambda, which may contain a closure. It's actually matched by way of the function, by way of automatic type deduction. So then it passes that into my zip width and properly returns the structure. And the reason for that is because this type F, whatever function it is, be it a function pointer or a lambda with possible stored state, constructs the right kind of my zip width, which it can then return. This all works precisely because it can do that type deduction. It does mean that with F possibly being a compiler time known type that I don't know, means that the structure itself is a compiler defined type I don't know, because it poisons that outer scope. But that's okay, because I'm using this as a throwaway iterator anyway. But the minute that I have to do this, where the function that I have to pass into this thing is not type deduced by the function call, I have no way of getting this type into this structure definition, into this type definition by way of generics. One of the ways to do that, because it doesn't have type deduction that goes all the way down into the, I can't use a type that's effectively derived inside the function to define the definition of the function on the outside. We don't have automatic return type deduction, so I can't do auto like you can in C++, and I can't return an impl trait because they have expressly forbidden that from inside a trait implementation. For reasons that baffle me. The two ways that they could solve this, they have not done, which is extremely frustrating. So let me see what happens. Let's go back to looking at this problem very briefly. So instead of doing a zip width, which does everything did I actually prove that that works? Let's actually take a look around for my zip width, see where else I've used it. I used it in my zip, but the lambda in question can be freely converted to a, probably because the types have to be known ahead of time, in trait. You'd think so, except that the whole point to returning impl trait is to get around that. I mean, you could make the same argument about a freestanding function, which I actually did in here somewhere. So I did an impl iterator, yeah, I did it right here. In merge, I don't know what the type of the iterator is, precisely because I pass in this lambda here in order to, hang on a second, does this capture any state? X and Y, no. No, it does not, but the sums to n does because of, because of t, right here. This t is captured state by one of the lambdas, by this outer move lambda. That's a function with code inside, so the concrete type can get inferred. Not if you capture a value. Oh, you're saying that's a function with code inside, so the concrete type can well, I kind of agree with that, except that all this is yes, it's a standalone function it's a root function that does not have any dependency on applying it to a particular. It's not trying to adhere to any sort of external implementation, but the type of this lambda is still not known until compile time, and only once it actually compiles the code. I can't choose a type that I can return out here that makes any, at the top here, that makes any kind of sense. For that very reason. Same thing in C++. Lambdas that capture state cannot be converted into function pointers. They are their own unique type, and you can't actually type it out at all. Only the compiler knows about it. The best you can do in C++ is capture that type information through other mechanisms. By way of like auto return type deduction, for example, or doing a decal type, but then it's still unique for each iterator, right? I still can't state it out here, and that's exactly why impl iterator works in Rust, is so that you can return something whose type is not exactly known, but you know that it adheres to a particular interface. Great way to get around the problem that this guy, and thus this guy, the entire structure I'm stuffing it into, the iterator itself, its type is effectively compiler determined. You put a compiler determined thing as an unboxed value inside of a structure, and the structure itself becomes implicitly compiler determined because one of its type parameters can't be specified directly. Just sugar for it, not in the return type, not in the return place. It isn't. Silent Z. It has a very special meaning in the return type position, and that's exactly the point. There is no way for me to write this code without this. I mean, if you can do this, please tell me how, because I can't figure it out. But as far as I can tell, when it is done in the return type position, its entire point is so that you return an object that has a concrete type, but that only the compiler knows about, and whose description can only be stated as a trait. This is not any kind of box type. It's not any kind of virtual type. It's a real type. Sort of a limited version of return type deduction. Except that the outside caller doesn't know what the real type is either. They just know that it happens to implement this trait. But you cannot do this. You cannot do this inside itself of a trait, and I don't know why. I kind of do know why they chose not to do it, but it's very frustrating because if I could do this, because there's no indicator of what kind of iterator it is in this return type. It just has to implement an iterator. If I could do that in... Where wherever the hell I put it. Where the heck was I monkeying with that? Right, up here. If I could, because this is exactly the same problem I'm having. If I could return impl iterator here, then I could daisy chain these two iterator definitions together. I could base one off of the other. And it's only because this is actually implementing it's implementing a trait, but the function inside the trait, the self type is fully known, the y's is fully known, the f I'm passing in itself is fully known. It's compiler generated, but it's fully known. But I'm not passing f into merge zip with as a type. I need to pass in this type, which wraps this lambda, this closure, which wraps another closure as the type. And the minute I did this, I'm screwed, because now we don't have return type deduction, so I can't return the version of merge zip with that should contain this, and I can't use the impl trait return type trick in order to not have to put any of this in at all. It's a restriction on the use of impl iterator or impl trait in that final position. Now, I can do this by way of boxing up an iterator using like dynamic dispatch and a couple other things. Looks like you are right. I always thought that impl trait was just sugar. Yeah, it is. It is in the parameter list. It is in the parameter list. It's just sugar, and it's good sugar. I like that. That's fine. But in the trailing position, it means something different. I'm using it as a type. I'm not using it as a trait as such. By saying impl trait in that context, what it really says is, I really am returning an object. It's not dynamic or anything. It's a value, but it's a value that is constrained in a particular way, and the compiler handles especially. And that's cool because it's very close to letting you more or less use fully unboxed things inside of structures. It's almost return type deduction or enough of it that it would make this work. It's so close, and I don't know a way around it, and it's driving me bonkers. Because this, to me, is a cleaner implementation of this. It literally says, you know what, my zip width is not going to do its own work. It's going to fob it off on merge zip width, which is exactly what I do in all three of my other languages. But there's no performance cost because there's no dynamic dispatch going on. It's all concrete types. No dynamic dispatch and no heap allocation. So close. And I mean, there is a cost. There's a cost to doing this, and the cost is, it's not a runtime cost, it's a type cost. The cost is by allowing you to do this and allowing you to put it like unboxed closure types inside of a structure, or passing them around as parameters. But especially inside of a structure, it poisons that structure. It makes that structure also compiler determined. But if you're going to construct something, use it and throw it away, like you often do in iterators, you just construct it on the fly, use it to process a bunch of data locally, and then throw it away. The fact that that iterator becomes a unique compiler determined type is irrelevant. I'd be perfectly happy with that. I'm going to make this look prettier. This is because it's reusing code, it's reusing the complexity of my outer iterator logic. To me, is prettier than implementing it manually. I mean, the real way to do it is to do it this fast way, obviously, if you're actually producing a library function. But for showing code reuse, this is unfortunate. Okay. I guess the next question is, if I did want to rewrite my zip, which deferred its behavior and my zip width, in particular, if I wanted to defer the logic off on it and off on my zip, but I did not worry too much about dynamic dispatch or
try to avoid a box type because that's heap allocation. But if I wanted to avoid a dynamic, or I didn't care about the dynamic dispatch thing, then where would I go with this? So let's say, that I don't have this. I don't have this version of my zip width. I'm instead trying to make something like something like, lost track of what I'm doing here. My brain has started to turn into mush. I'm trying to make this work, and this is going to implement my zip withable as a trait. And my zip is currently actually fobbing off on my zip width, except that it needs... Yeah. Get rid of some of the garbage code here that I have been futzing with for the sake of teasing out the fact that you actually can store unbox closure in the structures. I proved that. In fact, I'm currently proving this in running code. Some local siren color going on. Nope, no idea what's going on. Heading off down the highway. Alright. Or kind of a highway. Where are we? So... I am going to... This version of my zip is just a manual zip operation, which is the very beginning of my explorations, and now it's starting to clutter my code up a little bit. My zip width. Okay, so if I base my zip width off of my merge zip width, actually, this is going to just daisy chain into badness, because if I can't return a structure properly from my zip width, if I can't base my zip width off of merge zip width, because of the return value problem, because of the trait issue, what that means is I'm not going to be able to return from, I'm not going to be able to base my zip off of my zip width like I am here either. Because ultimately, and this is again the problem, I have to return effectively the same thing that my zip width returns. This is another problem that I'm starting to see, that Rust has a little bit of a boilerplate issue with the building of types, because in order for me to base my zip on my zip width, I actually have to find the type that my zip width returns and returns that, which is actually merge zip width. Like, this problem gets deeper and deeper, and I don't want my zip to have to know about merge zip width. It's too far ahead. I could probably do this. This is maybe just because I'm not familiar enough with Rust, but this might be able to be solvable with various kinds of wrappers, because there's some neat tricks involving constructing types that wrap other types at zero cost. And I haven't figured that out yet. But I actually have to convert this. Unless... Now, hang on a second. Here's the thing. You know what? I may actually archive what I have. I'm going to hit the magic of undo for a moment here. Let me. So this is my zip withable. We're going to get this in a running state and archive the software so I'm not losing code, because that would be kind of tragic. Hang on a second. Brain starting to short circuit again. This is the one where I just build my zip with structure and it comes up to here. And let's just get this building again. Alright, how far back do I have to get this? Oh, because I accidentally... Alright. Go find my zip width and scope. I've already mangled my code. I probably have. Let's just start backing this all the way up to the point at which I was actually just fixing my code up here. This is where I was cutting out some bogus code, so let's see if we can build that. No, I have to go further back than that. There we go. We're in a buildable state. I am going to reveal in File Explorer, and we're going to call this mergezip.back. We're gonna keep this alive. This is actually a working bit of code, and now we're going to go with so this is merge zip. What do we want to call this? The whole point to this particular thing was to try to do this with sort of no extra runtime cost, no dynamic dispatch. So I don't know, static dispatch, static comp. No, what's the right phrase for that? I'm gonna call it static dispatch, but that's the wrong phrasing I want to use. And we're not gonna have it as an RS because I don't actually want it built in here, so we're just gonna call this back. So now I'm free. Yes, that's fine. Make it. That's fine. Let's just, all right. So, what we're then going to do, now that I've made a backup, let's get rid of some of this cruft. Right. So my zip width goes as far down as here, and that's a working version of my zip width. That's fine. This is the one I would like to get working, though. This is a version of my zip that is not based on my zip width. And actually, what I may do here is I may comment out, so now this is not needed, which means this is also not needed. Let's just get rid of this. This is just some test code written at the end of the last stream to prove my point about structures containing unboxed types, and then that's still building. But now I'm going to take that out, and the reason I'm going to do this is because I want the zipping code to not complain, and I don't want it based on zip width for the moment. So this is a standalone zip function that does not try to fob off its responsibilities. That's a temporary thing. Why do I have a this constructs a myzip? Where did the myzip? Oh, because I need this structure. That's why that's missing. That's fine. So what I have done here is I've actually implemented a version of zip that does not require zip width, because I'm going to mess with zip width. Specifically, the only function in here that uses zip width directly is actually the dot product. This dot function. It uses, well, right now it uses merge zip width to do its work. I should probably come up with a version of this that only uses zip width. And actually, that's the problem, because the dot product should just be implementable using zip width, and then I would want it to fob off its responsibilities further up the chain. So what we're going to do, actually, is we're going to rewrite this so that instead of using merge zip width, we actually just use my zip width. We only need to pass it one function. We don't need to pass the action stuff. We actually just need to pass it a times b. And actually, just for giggles, let's make sure this still works using the built-in zip. And that uses a fold for the final part of the dot product, but we don't care about that. All right. Mismatch closing the limiter, because of course we did. Why is that? What did I screw up here? Because I don't need that. Function takes one argument, but two arguments are, oh, because I need zip width, not zip. So I'm passing in a predicate. Not a predicate. You know what I mean. Zip width found type parameter TS in the current scope, method not found TS. So no method found zip width found for parameter type TS in the current scope. Really? Really? Okay. Well, this is where we start breaking out the old... right. We're going to look up Rust zip width. Yes, please. Eventually it'd be nice. There we go. Yeah. That's a good question. Is there a zip width function at the... Don't actually want the struct level version of this. It's easy to replace this with zip.map. Oh, I see what they've done. So they actually suggest... Yeah, that's kind of a shame. I guess there's no... Except, is there a zip width? What do we have here, actually? No method... Oh, no method named zip width is found. Duh. All right, so they don't have a zip width. What they actually suggest is basically do a zip, which basically... so zip on V, which actually produces a tuple. The tuples of U and V, and then you do a fold. And the fold is going to be done over... Oh, they've actually already got a fold down below. So if I do a zip of these two, but don't provide the predicate... Kind of wish they hadn't buried these together, if I'm perfectly honest. But that's okay. We can just do it this way. This is actually going to be parameters Q and R. Can I actually... Here's an interesting question. Can I actually do this? A, B. I can probably do this. And X, Y. And then we're going to produce as a result... X plus, A plus X and B plus Y. Is it going to let me get away with that? Maybe. Could be exciting. Mismatch closing delimiter because of this. I don't need that in there. No. No, it is not. Oh, because I don't need the comma in there for one. It's not going to let me do this, is it? Destructuring in the lambda side of things. All right. The parameterless side of things. No, wait, the comma is needed because that's what it's listed as down here. So that's not the issue. Because I'm being dumb. No, because that's from the fold, right? That's the closing on the fold. Oh, that's what it's complaining about. All right. So I did get it right, maybe. And in fact, as long as we're doing this, let's just actually collapse this, because why not, right? So that is sort of the rusty way to do this, I guess. Expected parameter R found tuple. Oh, because I did R0 because no, that is. Hang on. No, I'm being silly. I don't actually have an A and a B here. What I have is the accumulator, which is the final result. I also have an incoming tuple, and I need A plus X times Y. I'm being so dumb. I could probably get rid of these outer braces. There we go. So this is how I might be expected to write a dot product using the existing things. Now, they do a zip and then a fold. They do a zip into tuples and then a fold. That's fine, except that it does build up that intermediate structure, which I don't really like. It's probably not the worst thing in the world. You can destructure just fine, but look at the line above. Yeah, thank you. I screwed that up. But I now got that working. That's not bad. I don't like the fact that it creates intermediate structure. But it is a tuple containing copyable values, and most likely to be integers. It could be references, but then I just copy the references, except then they couldn't be added. So this will work fine on the kinds of things that I want to do a dot product on. And it can probably do some optimizations cleverly, maybe, on the fact that I'm building up that tuple only to sort of immediately tear it apart. But I still want to write my mechanism in the way that I intended. And the only reason I'm uncoupling this is because my MyZip is going to explode. Most of this gets optimized out. It's probably correct. But in my version, I did the zip width instead of a zip, which immediately reduced it to effectively a string of single values. Like, it did effectively the product part of it first as a string of values, and then added those up without having to do any destructuring or constructing it in the first place. Is it better? I don't know. I'm just used to doing zip width because I have that in all of my other languages. Call me silly, but now I've done it the rusty way, so that's fine. That's a thing. Okay, and of course I could write a zip width using this, right? And there's no reason why I couldn't literally write my own zip width, and then I would just fob off on this, and then I would use that. In fact, let's do that. Let's say if I wanted to do a why not? Let's do the thing. We could do something like fn. Oh, except then I have to do the whole traits thing in order to produce an iterator, and yeah. See, yeah, that's part of the thing I'm fighting with right now. Is I can't build universally one iterator off of another without a lot of this boilerplate glue. I want to do effectively this eventually, where all I have to do, literally all I have to do, I have to have a trait just to do this universal thing, so it applies to all iterators. But then the only thing I have to do is this, and this just becomes an impl trait. Can't get there yet, so we're gonna do it the other way. What we're gonna do is I need, in order to base my zip off of its iterator structure, off of I can do one of two things. I can either do what I was trying to do here, where I have my zip width actually return a merge zip width structure and like directly build the target iterator. And the reason I can't build the target iterator directly is I can't specify the function properly. Not until I have impl iterator available to me. Or it does like full return type deduction. Can't do that. So the alternative is that I actually stuff the merge zip iterator in here and actually bury these two guys inside of it. That doesn't actually solve my problem directly, but what I'm going to do is I'm going to return. I want to avoid. Can I avoid the boxed iterator thing? If I do that, use the din keyword to create a dynamic dispatch. I think it has to be boxed up. Really hate that. Really hate having to box this. Various ways to return abstract iterators. Here's what we're going to do, though. We're actually going to do this. We're actually going to say the struct of myZip is actually going to create just one iterator, which is actually going to be the merge zip iterator. I'm then going to construct this funky iterator with its unknown type, but I'm not going to return it. I'm going to basically wrap it up in this thing. So basically, this is going to be IR. It's the iterator of the return type. Right. So the implementation is going to be is actually going to be my zip on item. It's going to be an iterator that takes no, it's going to be an iterator that takes an item. So it's actually going to be this is going to be more about getting the construction right than anything else. So what this is actually going to end up being in the long run is my next is going to be to return self dot IR dot next. And it's whining about that because expected tuple found associated type. Okay, I'll get there in a second. so this is actually just going to be based on the past in Iterator, right? The item in question is actually just going to be, I'm basically just wrapping this up. So it's actually going to be just A's item. I'm literally going to be stuffing a merge zip iterator in this. All right. Hey, look at that. The rest of that compiles. So this isn't the complicated bit of this. This is just boilerplate wrapper stuff. The trick is I got to be able to construct this properly. Okay. So this is going to return my zippable. So A and B here. I'm actually just going to call this. This isn't the A's and B's that I've been used to in the rest of my descriptions. In fact, I should be calling this X's and Y's, right, instead of A's and B's in the first place. Because I took some great pains to convert some of my code in the streams during the week. So I need to be able to zip two iterator types together. This isn't even my zip width. This is the problem. I have done this, except I'm going to base this on my, what do I have a working my zip width? Yes, I do for the moment. So I'm actually going to solve this. I'm actually avoiding the zip width side of this. Sorry, I'm avoiding the merge zip part of this. I'm only doing a link between my zip width, my zip and my zip width, and then I'll do the daisy chain up further later on. I just forgot what level I was at here. So basically my objective is to fob this off on a zip structure. So this is going to be where I have one iterator and another. I'm actually going to do a return a my zip that has as its type is literally just a wrapper. And actually, more to the point, what I actually want is I need to look up the concept of returning iterator from a function. Is a lot of those descriptions talk about how to return various kinds of iterators from functions, and I want to look up the various kinds of sort of dynamic dispatch I got going on here. Return iterator from function in Rust. What is the correct way to return an iterator or any other? Right, so this is sort of the problem, right? Is that I want to abstract away what's being stuffed in this thing. And as of 126, you can use infiltrate. I really wish I could. I can't return infiltrate here precisely because I'm already inside a trait. That's the thing that keeps killing me. So I can't use that problem. Box. If you don't mind using a little bit of efficiency, you can you can return a boxed din iterator. This may end up being the solution that I go at. This is the primary option that allows for dynamic dispatch. That is, for the exact implementation of the code is decided at runtime rather than compile time. That means it's suitable for cases where you need to return more than one concrete type of iterator based on a condition. That's perfectly sensible. The only thing I wish is that there were a way to do this that allowed you to stuff this thing on the stack or in structures, so that you could still have dynamic dispatch. But of course, the problem with that is you can't have that done in that way, because it's not a sizable thing. Like various kinds of iterators can be various sizes because it's not just a function pointer. Sorry, not just iterators. More to the point, the closures that drive them, and that's the thing that's killing me. It's not so much the iterator; it's actually the closure that drives them. But because my merge zip width accepts a closure, it's by definition going to be something that I cannot every one of my versions of merge zip with that iterator is going to be unique. And I'm okay with that. That's fine. Like if I pass in, the thing is, it's not going to be equivalent to one that's constructed with the same lambda several lines later. Well, unless I use the actual same lambda, but never mind. Point being, it would be nice though if there were a way to say, a way to pass around a typed reference to something that didn't need to be boxed. Alas, I don't think I have that option. So, new type. So what do we have here? So we have a wrapper. Their solution here is a wrapper this is kind of what I'm doing in a manner of speaking. So there's a lifetime on this, which I think is string split. It's a lifetime on the string. Implement the iterator. Implement iterator for wrapper. So that's more or less equivalent to my implement iterator. Implement my zippable. For not quite the same thing, is it? It's implementing. Here it is. Implementing iterator for wrapper is their equivalent, and I've got the item part of it, and I've got the next side of it. So I've more or less just implemented this bit, just because that seemed like the logical thing to do, except for the lifetime stuff. But I don't think I have lifetime issues because I'm doing values at the moment. We'll cross that bridge when we come to it. So the function toWords returns a wrapper type with an. Can you even do? No, that's auto deduction on the lifetime. It's not a parameter. So the wrapper doesn't. So that's just lifetime stuff. So the wrapper itself isn't templated on anything. So their objective here is to wrap an iterator, wrap a wrapper around an iterator, and then do an implementation. So this is new type. This is the new type syntax. All right. This might be where I go with this. If in order for this to work, though, there has to be a way to take the string and you wrap it up in this wrapper first. So the thing that's tricky is that I want a function that can take any iterator on the left to be used as the input to this thing. If A is an iterator, this is the mechanism that actually enables me to construct this from any two pairs of iterators. Is this significantly different from what I see here? Well, yes, because this is not turning. This is not implying a trait. I don't even know what I'm saying anymore. Okay. I need to be able to say, in order for this to work just like all of the other iterators, to keep the syntax the same, using a new type means that yes, I can, once I've constructed this, I could use this as an iterator in its own right, but that's all I've really done up here. The other half of this is to construct it in the first place, and the way they do it is through a two words mechanism, which is an explicit function call to make that happen. That's what I want to get around, or to implement the same way that I've been doing all this time. Right, here we go. So my zip is going to have to be, if I have the two iterators in question, the iterator in question So I really haven't done a new type here. This, by the way, is specifically about returning the iterator types and not necessarily storing it, but I find that the two of them often share similar properties. What I really want to be able to do effectively is create the object with the appropriate type inside of here. That is base my zip off of what my zip width is going to return, but then hide that information from my zip. So does the wrapper approach let me do that? No. The reason why is I'm explicitly having to return the wrapper here. I want to be able to hide that information. See, that's the problem. If I have to hide it and I can't hide it behind automatic return type deduction, this actually requires me to specifically state the type. The only way to avoid explicitly stating the type, the only way to avoid explicitly stating the type and not use a boxed din mechanism is to have an impl trait here. Because we don't have return type deduction. So here's what we're going to have to do. We are actually, let's start with the boxed solution and see where we get to. So the type of the return here, now this is fine. All right, so I'm finally starting to make a little bit of progress in my mental thinking about this. Like, I'd like to do this without any of the boxing, but I can't. Let's just get that out of the way, out of my head. But if I have to have a type in the return type for this thing, and I can't do impl trait because that's not allowed inside a trait for reasons that baffle me, I can do this. And specifically, I can do, so this is din iterator, but this is the value of the associated type must be specified. Yes, it must. But that I do know. I don't care what kind of iterator it is, as long as what it can return is a tuple of a : item and b : item. All right. So that is what this guy has to return also. No, actually that's not what I want to do. Actually what I want to return is this guy. Right. So for this to work, I don't want to return that directly. Actually, do I want to return that directly? Let me think about this for a second. I actually may not need all of this stuff. If I have to go to all of this trouble anyway, in order to box this thing up, and I construct a merge zippable, a zip with object, a zip with iterator that has the appropriate properties, the heck I need all this for? Because I don't need to, yeah, okay, so, box, so the result of this is going to be box new, with the type, box : new, and instead of a structure, the thing I'm going to provide in here is basically my zip with except this is going to return a box on an iterator, and the problem with that is no, it's still going to be owned in main as a boxed type, which itself can auto dereference just like a regular reference. Ish. I mean, you can see it here in this example here. 2 words ultimately returns the result being a boxed in iterator item, and then it's got some lifetime things, which I'm sure I will have to sort out shortly. But then it's just being used as an expression in here, which then cleans itself up because things clean themselves up in this in Rust, which is fantastic because of the ownership stuff. Totally love that. So we're going to call my zip with, and we are going to pass in. So it's actually XS. I'm going to get here. And we're going to have X and Y, and we're then going to have that produce a tuple containing XY. Which is probably not going to work, but let's find out where it explodes. Main function is not found because I have not closed something off here. Let's go and figure that out. Well, first of all, doesn't need that semicolon. Okay. All right. So I'm missing a brace somewhere in here. One, two, three, 2, 1, 0. That one's balanced. That's balanced. Looks like impl trait and trait definition works on nightly, so at least plan. Oh, yeah, no. So, hey, Silent Z, you make a very, very good point. I can't do it now, but in the description for how impl trait works, just for anybody else who's watching this video, they implemented impl trait because they knew they were going to need it. They didn't want to go full return type deduction, and they wanted to make impl trait because it was a slightly scary change to the language, and I totally agree why. They didn't want to implement it in all possible conditions. They found it was safe to do in the top level functions, if you want to call them that, plain functions case. But not an impl trait, but they did imply that it was a possible place where they were going to do it. Yeah, the minute that becomes possible, this becomes a bazillion times easier and very pretty, because then you can get this kind of daisy chaining of responsibility of iterators, but without having to do wacky wrappers and without having to incur the cost of this boxed in that I'm going to do. But I'm going to do it this way because I still want to make this work as daisy-chained operations, and ultimate performance isn't the issue now. I've kind of shown where I can go with that using it. So anyway, back to work. It is very cool though that they do have that planned. I just hope it becomes permanent. I hope they actually say to heck with it and just do proper return type deduction, to be honest. But I understand how that's kind of tricky. Don't blame them. Don't blame them at all. Except that it makes stuff like this a little bit more difficult. What I want actually is a way to reduce more of this boilerplate, because it's great to be able to say impl trait, and that cuts out a lot of the boilerplate. But then you're going to see an explosion of doing that, not because it's necessarily the right answer, where an explicit type would be preferred, but because the types are so ridiculously long and it's kind of hard to introduce type aliases at the right point in the code, you can't shorten it, which is a little annoying. But that's a minor quibble. Not going to worry about that. The next problem, though, is where the heck did I lose a brace? Because this is a new fresh hell. Oh, come on. I want to do that. Thank you very much. So it's somewhere in this. I'll be super blind until I figure this out. It's not in there. So expected std box found. Oh, I see. No, I don't see. What did I screw up here? Din, open brace, those, and close brace. Mismatch types. Why is this a mismatch type? Because did I change the type up here? Super excited about that impl trait thing. Okay, I'm gonna pour myself more liquid. I'll make this work. This is super exciting. I have been chuffed about the fact that I got merge zip with working today. Actually, I had it mostly working yesterday. I almost couldn't sleep. I was so excited. Didn't quite work. I found a bug this morning if you were here at the beginning part of the stream, but we fixed that in short order. And yeah. And one of these days I'll have to fight with the bar system more than I currently am. Okay, I'm going to take a 2-second break, and I will be back. So hang in there. All right, ladies and crazy people, we're back. So excited about getting all this working. So here we go. Let's go back to Code Weaver. No, that's not the right thing. Here we go. Coding. Aha! Got the right button. All right. Let's try this again. We are all the way back. We are looking at why this is complaining to me now. We should actually shore up these naming conventions so that I can spot what's going on. This should be X's and Y's, but I'll fix that in a minute. So let's go to the terminal. Let's actually get a slightly more verbose version of what the heck's going on here. Mismatched types implicitly returns blank blank as its body has no tail or return expression. Oh, is that all you're complaining about? Well, that's annoying. So if I do this and I do std found unit type, that's fine. Don't know which crate the silly box thing lives in. Okay, so let's let it lead me. I don't need the arrow. I am smart. I am smart. SMRT. I am smart. So, cannot find value XS in this scope. That's because I'm not using X's and Y's. So let's actually start to do this properly. Right, so that's, yeah, okay, so. Except that's self, actually, which is my X's, but that's all right. What's our new fresh error? May not live long enough. The associated type B may not live long enough. Consider adding explicit lifetime bounds. This is now where I have to start dealing with bounds issues, precisely because I'm starting to deal with boxed dins. So, charming. This is where I'm going to start to look like a noob all over again, because ladies and gentlemen, and others and so on, I actually have managed to dodge that for most of this project because I've been working mostly on values that can be copied. I've had to deal with copy traits and the like, but all right. So let's take a look at this. The associated type B as standard iterator item may not live long enough. So I need to basically state that Okay. Actually, the A item may not live long enough either. All right. Here's where I learned a new headache. Still a good thing, though. All right. Let's go. Rust. Lifetime. Parameter. Sure, why not? Yes, so preventing dangling references with lifetimes. Aim of lifetimes to prevent dangling references, which cause a program to reference data other than the data it's intended to reference. All right. This is going to take me a little bit of time to read. Do I want to do this while I'm on stream? Probably not. I need to impose thing is, though, why do I have a lifetimes consideration here at all? I am basically calling my zip width to construct the iterator type. I'm passing in this lambda as a value. It's going to be moved in. Oh, because no. Generic lifetimes and functions. So write a function that returns the longer two string slices. Right. So in the example that we have here, the very simple example of I've got references coming in, I've got a reference going out. It's going to return one or the other, and it says that it contains a borrowed value, but the signal, the signature does not say whether it is borrowed from X or Y. Consider introducing a named lifetime parameter. And basically what this does is it enables me to tie the lifetimes together. When we're defining this function, we don't know the concrete values that we passed in, so we don't know if the if clause or the else clause will execute. We also don't know the concrete lifetimes of the references that we passed in, so we can't look at the scopes as we did in the other listings to find out whether or not the reference we return will always be valid. The borrow checker can't determine this either because it doesn't know lifetimes of the action y's relate to the lifetime of the return value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references so the borrow checker can perform the analysis. Okay. Thing is, where are we using references here? We are not taking self by reference. I mean, self may be a reference, but then we're not taking that reference by reference. Anyway, self is not taken by reference. Wise is not taken by reference, but I don't think my zip width takes anything by reference either. No. Right. So hang on a second. I want to rebuild that so that the terminal window error is not got cruft in it. So the type my zip width A, B, and closure. Type B may not live long enough. Yeah, the recommendation to start adding static lifetimes to this is not what I'm after. The associated type may not live long enough. The associated type A as item may not live long enough. The associated type B may not live long enough. So I need Y's to live long enough. Because the lifetime of the iterator, let me work this through. The lifetime of the iterator, lifetime issues with closure, time to slap the move keyword and hope that fixes it. No, I refuse. I refuse. Also, this particular, I have to know what's going on. I know it's a common trope, at least it's been so looking around the boards, that you start adding tick marks and moves in order to eventually make everything compile. I have to know what's actually going on here. But here's the thing. With this, the closure itself is self-contained. It's not capturing anything from the outside world. It actually really is a function pointer in this case, for all intents and purposes. More to the point, yeah. No, still have to figure this out. Yeah, that's an interesting problem. Lifetime issues with closures. It's going to be fun, and I'm going to have to start reading up on that, but I'm bound and determined to figure out how to make this work. And it's unfortunate that I sort of come into Rust not practicing heavily with lifetimes in simpler contexts. Yeah, throw me into the fire, apparently. So yeah. So here we go. We're going to try doing... we're going to try saying that we need the iterator to have the same lifetimes. I'm going to use this as an example. I need the iterator that I output to have the same lifetimes as the two parameters that I'm coming in. Let's start there. So... So this is going to be lifetime and trait objects must be followed by plus rest. What? Trait objects without an explicit din are deprecated. Okay. I think the iterator should have static lifetime since it contains no references. All right. Let me look up static lifetimes. Static lifetime. Rest of a few reserved names. One of them is static. You might encounter it in a few situations. Reference lifetime. As a reference lifetime, static indicates that the data pointed to by the reference lives for the entire lifetime of the running program. It can still be coerced to a shorter lifetime. There are two ways to make a variable with static lifetime. Both are stored in read-only memory of the binary. Well, no, I'm clearly not doing that. So trait bound means the trait does not contain any non-static references. E.g., the receiver can hold onto the type for as long as they want, and it will never become invalid until they drop it. It's important to understand this means that any owned data always passes a static lifetime bound, but a reference to that owned data generally does not. Ouch. Here we go. In this example here, so if I say impl debug plus static, okay, so the value that gets passed in impl debug, again, just being sugar in this case, it's basically just saying it's a generic type that implements debug, but it's saying that the passed in value also has to be static. So in this case, I is owned and contains no references, thus it's static. And in this case, oops, I only has a lifetime defined by the scope of main. So reference I only has a lifetime maintained by the scope of main, so it's not static. So I understand why that's interesting. Okay. I think it's the second case you're looking for. All right, no, yeah, I actually kind of think that's not completely ridiculous. Does my iterator contain, is my iterator guaranteed to contain no references? I'm not sure that's actually true. And the reason why is because I can't necessarily guarantee my merge zip with iterator contains itself other iterators which themselves may not have static lifetimes. And more to the point, the closure might as well. Okay. In which case, this would be, I guess, boxed in iterator plus static as a bound, but incorrect braces around trait bounds. Okay, you tell me how I do that. Boxed in iterator. Oh, right, because the braces are part of the. Never mind, I'm being dumb. Thank you. Expected a path. Oh, no, outside the brackets. One more. Almost there. Incorrect braces around trait bounds. All right, hang on. Gotta look a little closer here. Oh, because I still have... no idea if that's gonna work, but... it certainly didn't help significantly. Alright. I'm a little suspicious of this only because, I mean, I can see how it operates in the case of I. I see how it operates in the case of I is owned and contains no references as a static. So I gotta reread this. It says, as a trait bound, it means the type does not contain any non-static references. The receiver can hold on to the type for as long as they want. It will never become invalid until they drop it. That's... Is that true? The iterator, that is not actually true, because an iterator is going to contain effectively a reference to the container on which it operates, is it not? In which case, if the vector goes away, and arguably any dynamic memory it's allocated goes away, then that iterator is not valid anymore. That would be my reasoning, because I'm literally holding on to iterators, and they are effectively holding on to is a bad way to say it. I'm holding on to iterators, but they are referring to containers. I don't think static is going to work here. Based on that description. I mean, no, you're right. Actually, you're right. Iterators don't have to attach. Iterators can do anything. Iterators can just sit there and count. Iterators can generate random numbers. Iterators can arguably build new stuff out of nothing. Like, they could output a list of elements that eventually go into a collection. Like, yeah, anyway. No, you're correct. But that does mean that I can't use static here, because I'm pretty sure mine is not static. I'm pretty sure mine is based on containers, especially when used in the context that I'm using it. I can't guarantee that the structure that I'm going to be fobbing this off on contains no references. Especially because ultimately I'm going to daisy chain this all the way up to merge zip with eventually. I don't think I can do this. I think I have to do the lifetime another way. I have to say... I mean, I could be wrong, but I mean, I'm not getting useful results out of the attempt to build with just that. So I have to think this through. This is going to take me a while to figure out. I'm not going to lie. This is... Whoops, that's not where I want to put that. Actually, I may have to, because I may have to have the lifetime also associated with... Okay. All right. I'm going to put that down for the moment, but I am going to come back to that because that's an interesting optimization to think about. I actually like that. Lifetimes and function signatures. Thinking in terms of lifetimes, yeah, this is going to be fun to figure out. Lifetime annotations and struct definitions. Oh, here we go. This is interesting. We've only defined structs to hold owned types. It's possible for structs to hold references, but in that case, you would need to add a lifetime annotation on every reference in the struct's definition. This has a struct named important excerpts that holds a string slice. As with generic data types, we name the type of the generic lifetime parameter inside angle brackets after the name of the struct, so we can use the lifetime parameter in the body of the struct definition. The annotation means an instance of important excerpt cannot outlive the reference it holds in its part field. Perfectly sensible. There's also an interesting thing about lifetime elision. You've learned that every reference has a lifetime that you need to specify lifetime parameters for functions of structs that use references. Chapter 4, we had a function which is shown again that compiled without lifetime annotations. The reason this compiles without it is historical. In early versions, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signatures would have been written as such. Alright, so that's where you can more or less exclude having to deal with the lifetimes, but the compiler uses 3 rules to figure out what lifetime references have when there aren't explicit annotations, which unfortunately can't be applied here apparently. I will go and read that in more detail later. Lifetime annotations in method definitions. Here we go. We use the same syntax as that of generic type parameters. Lifetime rules for struct fields always need to be declared after the impl keyword and then used after the struct's name because those lifetimes are part of the struct's type. So as part of the impls type here, we have the same problem. We need to bring into scope a lifetime. So there's our lifetime. And my zippable also has to be so this says this trait takes 0 lifetime arguments when one lifetime argument was supplied. So that also implies then that I have to do a lifetime parameter for this, and that makes sense. So that's fine because I have to think about it this way. A lifetime generic parameter, or sorry, a lifetime parameter is part of the thing's type. That's interesting. I actually found it really interesting they implemented it that way. Okay. And actually, this goes on to talk about the static lifetime too, but I'm going to try to avoid basing this on static lifetimes. I don't just want this to compile. I want it to be something plausibly practical. The lifetime parameter declared after impl and its use after the type name are required, but are not required to annotate the lifetime of the reference to self because of the first elision rule. And the first elision rule was back here, so let's go take a look at that. So it says the elision rules don't provide full inference, but that's fine. The first rule applies to input lifetimes, and the second and third rules apply to output lifetimes. So let's actually take a look at this very quickly here. If the compiler gets to the end of the 3 rules and there's still references which we can't figure out, the compiler will stop. Well, okay, sure, fine. The first rule is that each parameter that a reference, each parameter that is a reference gets its own lifetime parameter. In other words, a function with one parameter gets one lifetime parameter. A function with two parameters gets two lifetime parameters, and so on. The second rule is if there's exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Okay, that's perfectly sensible. The third rule is that if there are multiple input lifetime parameters, but one of them is self or mute self because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes methods much nicer to read and write because fewer symbols are necessary. Okay, let me think about that. Third rule is if there are multiple input lifetime parameters, but one of them is self or mute self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. That implies that any output we have can only last as long as the lifetime of the thing we used that caused self to be produced. Now, I could probably, I'm sure there are ways to override that, but let's pretend we're the compiler. We'll apply these rules to figure out the lifetimes of things. Okie dokie. I will have to read that in gory detail, but I can do that offline. I think. We'll find out, won't we? Okay, hang on. What are the other rules here? Let me just double check what's going on here. So, second rule is that there are exactly one lifetime. No, okay. So the third rule is if there are multiple lifetime parameters and one of them is as. All right. So I already read that. So here is an example where the third lifetime elision rule applies. There are two input lifetimes, so Rust applies the first lifetime elision rule and gives both self and announcement their own lifetimes. Okay. Then, because one of the parameters is self, the return type gets the lifetime of self, and all lifetimes have been accounted for. It's sensible, and in fact, I haven't had to do lifetime production at any point. Okay. Okay. All right. So based on that, what we know is that in the absence of these annotations that I've started adding here, self and wise would both have their own lifetimes. Let's see if we can figure this out from the rules. Second rule is if there's exactly one input, doesn't apply. Third rule is there are multiple input lifetime parameters, but one of them, now they're both implicit in this case, ignoring the tick A's that I've just added. But one of them is self or mute self. Because this is a method, the lifetime of self is assigned to all output lifetime parameters. Okay, so the lifetime of self is going to end up being the lifetime of the box. The boxed value. Okay. It's interesting. I have to, however, figure out why merely the act of wrapping this in a new associated type may not live long enough so that the type my zip width, etc., will meet its required lifetime bounds. Okay. Okay. Let's see if we can figure out Rust lifetime closure. How to declare a lifetime for a closure argument. All right. So in this case, cannot infer the appropriate lifetime. Okay. How do I declare for this closure? The mute split white space is actually... Okay. I don't think I'm going to quickly be able to deduce it from that particular example. Lifetime annotation for closure argument, lifetime with closure captures. Yeah, so we've got piles and piles of version of this. Apparently lots of people fight with this. Well, you kind of warned me about that, Silent Z. If you return a closure, which I kind of am, I'm returning a closure inside something else. You have to make sure that the closure has everything it needs even after returning, after the temporary function parameters are popped from the stack. Thus, I think you want to move the stuff you return into the closure. Well, what did he actually do here? Okay. But why the move? Because I'm not capturing anything outside of the closure in this case. And until I wrap this in a box new, I didn't need to actually do any of this. Functions defined inside other functions are static. They're not even connected with the outside code. Yeah, that's fine. Consequently, their lifetime parameters are completely independent. You don't want to use tick main as a lifetime parameter for get chunk because it will shadow the other outer main. Okay, so this is talking about this specific example. Next, about closures. This expression does not really do what you think it does. Closure function arguments allow irrefutable patterns in them. And ampersands have special meaning in patterns. Namely, it dereferences the value it is matched against, and it assigns its identifier to the dereferenced value. Alright, so yeah, that's an auto dereference syntax, which I really wish they hadn't overloaded the meaning of that, but alright. You can think of ampersand a pattern as the opposite to ampersand an expression. I guess I can kind of see that. If you're deconstructing something in a pattern, then having an ampersand in there should deconstruct the reference wrapper, if you will, around the object. So that kind of actually makes sense. Mute, however, does not belong to ampersand and patterns that belongs to the identifier means that the variable with this identifier is mutable. Oh, interesting. literally the spacing matters, that's terrible. Okay, never mind. First of all, you should read the official guide, which explains ownership and borrowing and when to use them. Anyway, your problem can be solved in a much simpler and generic way. Yeah, but that's not really answering his question. Alright. Specify rushed closure lifetimes. It's going to be talking about futures. That's lots of fun. That's something I've seen before, actually, that I don't understand fully, is the for syntax on. No, I say for lifetimes. Yes, see, for lifetimes. I do not know the syntax, and I should figure out what that means. This is going to be the next stumbling block to make this work. Not that specific syntax, but lifetime constraints and closures. Lifetime and closure captures doesn't really apply here. Yeah, right. So, for closures that move, the move in front of it. Let me see if I can recall what that means. Effectively, closures capture any surrounding context by reference by default. And that's fine. It just means that the closure can only last as long as the things to which you're taking the reference. However, the move command in front of it, or the move keyword in front of it, says capture these things by move instead, and provided they're movable, then the closure now owns those items. Couldn't really replicate your myzip with but. Ooh, shiny. Wow, that's really shiny. Wow, okay. I think the problem is not in the closure, but the missing lifetime animation on A and B. Yeah, I kind of got that, and the reason why, and don't get me wrong, I did not solve this in any sense, and I'm going to be looking at your code really closely. Because the lambda does not capture anything outside itself, it is essentially self-contained. If I captured anything, then it does make sense why that might be a problem, because then the thing that you're capturing has to have the same lifetime as wherever you're stuffing the closure into. So missing lifetimes animations on the A and B iterators. So once again, Silent Z, do you have any objection if I show your code on stream? Because that's actually really good. I'm going to have to actually, if I do that, I'm going to have to pull up. Of course not. Okay, I just wanted to be sure. How about this then? If you send something like that to me on the stream, I will maybe have carte blanche to show it unless you tell me otherwise. Is that acceptable? Because I don't want to have to keep asking you. I mean, I can keep asking you. It doesn't really bother me, but yes. Okay, so let's go and quickly pop over onto the stream on this box, because I don't normally do that. Go into the video producer, pull up the chat. There we go. Now I've got it in the right spot. Now I'm going to pull that over off onto, I guess I can stop using Programmer's Notepad and just dump that in here. So, hope everyone can see that. Yeah, I'll probably, I'm going to study this for a second, because I'm I wouldn't want to share links if I didn't want people clicking on them. Hey, you know what? Fair point. Although this is going to live on in perpetuity in my video, even though the chat's going away, because I don't record the chat anywhere. So there is one minor difference with that. But we are where we are, so I'm going to close that, and I'm going to take a look at this. So yeah, so there's been some bounds work going on here. So trait my zip, yes, so I was slowly getting there, and then I had to say that the iterator had a specific lifetime that was tied to that, rather than having its own. And then the B iterator also had that lifetime. That's pretty cool. Yeah, I totally get that. And then we wanted to make sure that that's interesting. So you've actually got, correct me if I'm wrong, but you've got a lifetime on the box. Because you've already effectively bound A, and so you've implicitly bound A item. And so you've effectively bound, I guess, the iterator in here. This is interesting. Okay. So let's annotate my code very similarly to the way that we have annotated yours. I was gonna get there, never, because maybe eventually. Okay. This makes sense. Bind, because everything has an implicit lifetime. Alright, so, that is not what I wanted to do. This is the one part of this language that is going to take me a while to master because it's unlike anything in any other language. Or at least anything that I've done. And as a side note, that's actually kind of why I'm learning this. Languages occasionally have clever ways to reduce doing complicated things or to make hard things that should be easy to express. This arguably makes some things harder to express, but it's actually new. It's kind of a very new way of approach to memory management as far as I'm concerned. I find that fascinating. All right, so this is what was done here. And I absolutely want to understand the intricacies of the way Rust does this. I want to see what its value is, and I've completely gone off script. Where are we here? So you didn't have to annotate the box's description here. You didn't have to annotate self because its type is coming from effectively one of the parameters being used for this, actually, right here. And A is known to be an iterator of the right bound, so that's why self is so bound. Okay, we're going to get closer here. Thank you for that. You have no idea how much that helps. All right, so let's slowly start to get here. The iterator B may not have a lifetime, and now it's only B that's the issue, and because, why? Because this has to be, Y is a B, but B has already been constrained to iterator plus tick A. So where have I missed? Right here. Isn't that cool? Silent Z, very well done. Thank you for supplying me that critical piece of information. And now that I look at it, now that I've done the transfer and studied the error conditions, it makes sense, right? So here's what we've learned from this. God, how awesome is that? Here, the fact that it built is just great. Here's what we've learned from that. First of all, okay, so it couldn't deduce the type annotation for lifetimes correctly because it. Let me see if I can figure out how to describe this. So. Okay, here's the thing. Actually, there's a bit of the syntax that you can't really annotate the parameters directly since they are not references. True. Okay. Actually, I'm going to have to understand that sentence more clearly as I go along. But okay, so here's the thing. Why was the okay? So here, let me think about this a second here. We had to so this is just basically just one of the generic parameters, and that's why that's there. Okay, so we're stating that the iterator has this lifetime. Both of the iterators have this lifetime, and as a consequence, we want to bind. And this is the bit that I can't quite figure out is why we have. Oh, hang on, no, it is this. This tick A is actually inside the box, and so we've said and this is basically what you were doing earlier. So now it makes sense. So we're basically saying we're returning something with a box dynamic iterator that a boxed item, which is a dynamic something. In this case, that obeys the composite trait of the iterator with these types plus the lifetime, which is how I tie the lifetime to that the trait object that I'm basically building inside of this box. Okay. Fascinating. And I'd lose my geek cred if I didn't say captain after that. So the this is a composite trait, one piece of which is this trait bounds. That's interesting. Sorry, not trait bounds, lifetime bounds. That's interesting because here, this is being used as a trait. I guess it's technically being used as a trait everywhere else as well. Very interesting that they... Alright. Well, it's being used in the position that would be typically considered a trait. I don't know if that makes it a trait. Lifetimes are their own thing. Lifetime... Okay. Wow. Okay. Alright. Well, first of all, let's actually run this thing and see if it actually works, because I actually kind of expect it will. Yeah, so there is the zip function being applied. It's the second pair here. And actually, I still have the... There we go. So it's running all my code. But the key points here are it's actually doing the zip correctly. And I did not have to... So we can actually get rid of this, because we didn't need to wrap it up in anything, precisely because in boxing something, it can be automatically dereferenced with that dot operator. It effectively... that effectively makes it so that anything I return by... Anything in principle that is a reference or a boxed item can be treated as the underlying object itself in that kind of syntax. That actually makes the calls a little bit less strange. I don't know if I like that, but it certainly saved me here. So I have to... So clearly my next major learning is mastering lifetime analysis of this stuff and where to tag that knowledge. A lot of reading for me later. But hey, you know what? Let's continue on this, because now this same trick we can use to daisy chain the zip width operation. So the problem here is that we have zip width basically doing all of its own wrapping here. And I don't want it to do this. I actually want zip width to fob off its behavior on merge zip width, because I've shown in the other languages, and arguably here for that matter, actually I haven't shown it here, but I've shown it on the other languages that effectively I can build zip width out of merge zip width because it's strictly a superset of solutions. So what I want to do actually though is I want to get rid of all this boilerplate to do all of that logic, comment all of it out, and implement the zip width version of this, which further fobs off the problem of doing the zips on my function. Is this efficient in runtime? Well, partially runtime cost because of all the dynamic stuff I'm doing, but ignoring that, no. You would not do this in a practical sense in like a tight library. But for the sake of correctness, there's exactly no reason why we shouldn't be able to do this. And so, because I shouldn't have to know in here how my zip width is doing its work. I can't do it statically, but I can at least do it dynamically. And literally everything else in here should remain the same. So this is going to be self.merge zip width. It's going to be a little more complicated than this, but we'll get to this in a second. This is actually going to be... it's going to be a myZip withable. Merge zip withable. This is going to actually have to be a little more complex because it's going to have to take the... it is going to have to take the... Actually, it doesn't. Hang on a second. Let me think about this a second here. When I wrote this one, I did not have to refer yeah, no, this is fine. This is fine because I'm just basically returning a boxed iterator of a type that can produce. This is wrong though, because this has to be the result of... oh, this is going to be interesting. It has to be the... we have to have the return type and the function as a part of this. So we are actually going to want to grab ys, f, and r. So we're actually going to start calling these the right things now. Actually, no, maybe I won't. So this is B, F, and R. I'm sure there are going to be lifetime associations with these as well, but we'll cross that bridge in a second. We're going to take self, ys, and f. Boxed in iterator, this is not the right item. Oh, yeah, so this is going to be item equals r, so that has to be a thing that we do. Right. I have to have a where clause in here because I don't want to bury this all on the same line. So actually, you know what we're going to do? I'm going to leave this up here, but I'm going to put all of these types that I have to constrain in some way on their own line, because I think that's going to make it easier for me to read what's going on here. So, do I have my where in here? No. Where? Exciting! Yeah, so f is going to be the function description here. We're definitely going to have some lifetime analysis because the function object itself has to last the appropriate amount of time. Right, and then we also want r. Oh, except that's implicitly defined. Okay, so r has to have its own constraint, which is probably going to have to be a lifetime. But we're going to leave that out for a moment because I want to see the errors that this gives back. Right, so now let's clone this into here. Except I've got X's and Y's here, so this actually has to be A and B. Should have stuck with my X's and Y's. Oh well. So this is going to be self.merge zip with, but the function call is wrong. Right, so we're going to do something that looks like this. There, that looks a little prettier. And then itself, actually I'm going to move this up here, actually. Hang on. Brain has started to short circuit with too much bracketing. So the value that we're going to return is box new. I'm going to pop this up to here, take off one of those, add an extra one of those here. Just trying to get everything to align a way that I can sort of follow. Except these parameters are going to start going on their own individual lines. There, that's what I want. Now this is going to have to be a function that that does the that produces a function of the right type based on the function that I've been given. And doing a zip with, we're also going to do the fact that we don't want anything to be done to the tails. So this is going to be a none. Actually, it's going to have to be a tuple because it's going to be, you know what, just stop and none. And then we're also going to do another one of those, actually. So this handles the tails. And now I understand the meaning of your sentence island Z, of course. In some of the examples in the code, this, in fact, right here, you can annotate references with individual, with lifetime parameters, but you can't do that in the cases that I'm talking about because I don't know if they're references, and it doesn't apply to non-reference. I don't think you can apply that syntax to non-reference types like you're talking about, but I can apply them as part of the trait. So that now has gelled in my head. I get there eventually. So this is not the right function. It's going to tell me that no method for parameter A in the current scope because it's not labeled that. It's labeled merge zip with. Thank you. Copy is not implemented for the items. That is a very good point. As part of some of this operation, I specified that the types, so for merge zip with, I specified that the types had to be copies. And this was just to make my life a little bit easier. On the items in particular. So I will pull that down into here, and I'm sure that's going to daisy chain outward to my other functions, but I'm okay with that. That's fine. So what that means here is effectively it's actually A item and B item have to implement copy. And that's an interesting point, actually. If I have constrained A and B's items to be copied, do I even need the lifetime parameters anymore? think about that. Right. Actually, that's A's item and B's item. So that's fine. And we have problems, but I knew that. So mismatch types, expected enum. Oh, yes, because I don't have the right functions going in here. So this actually is a tuple containing the action that I want to take, which is always going to be mzw step both, followed by sum of. And in here, I actually want an extra set of parameters, one of which is the tuple for x and y, I think. Type mismatch. Again, expected parameter r found tuple. Oh, because I don't need the return value to be passed in or deduced. I actually know what it is. So this is actually item equals... no, hang on, I don't. I'm not doing zip, I'm doing zip with. I do need R. So, it's sum of F. Hang on. It's actually going to be... Actually, I don't need to do this. This is going to take... No, I do. Zip always returns... So the function that I'm passing into zip with, the function I'm passing into zip with doesn't have to deal with sums or nuns or whatever. There's no filtering going on. I don't have any of that magic. So it's actually f of x, y. Now I have too many braces going on here. Mismatch delimiter. Okay, that's fine. I think I have... There we go. I think that's right. 7 problems. The parameter f may not live long enough. Now, we knew that. Ha! There we go. We knew that. We knew that because, for the same reasons that we're talking about all of the others, the f type that we're passing into all of this has to have its own lifetime. That's associated with everything else. It has to live at least as long as the thing I'm stuffing it into. So, because it could be a function pointer, but it could also be a closure that contains captured state that has to have lifetime. And so I'm basically fobbing this off and saying that the closure has to last this long, and then the closure can take care of the rest of the effective lifetime analysis of this. So f is this guy plus tick a. Right, so impl has stricter restrictions. Yes, it does, because I have to do it up here as well. Totally reasonable. The trait bound copy is not satisfied down here. So this is going to daisy chain down into here. And so the interesting question... Actually, the copies didn't save us from... actually, I'm going to test that out in a moment. What I'm going to do is I'm going to say... yeah. Now, if I really, really fully want to understand this, I should probably find a way to make this so that it works on stuff that doesn't have the copy trait. But there's only so much my patience can handle. So here we go. We're going to do that, and then we have to have the same where constraint here. We need open brace there, but no closed brace, and get rid of that one and add a where. How are we doing? One problem. Closure may outlive the current function, but it borrows f. There we go. Now we are finally in a position where we're dealing with a closure that has to manage its lifetimes. So, do I want to move f in? I actually can in this case. I don't have to have a reference to f. Oh, no, but that doesn't matter because f itself could contain something. I don't think making this a move closure will work. Oh, hello, maybe it will. I have to think about that. One of the lifetime elision rules is triggering here, I expect. F is already known to be of some type that corresponds to this, that has the lifetime of the thing. That has the lifetime of A. That's already been sorted. So F already has the appropriate lifetime. Wow, this is gonna make my brain hurt. Why is it that when I remove the move on there? So what that's then happening is it's capturing F. It has to capture F. It's capturing F by reference. That's the reason. And it's capturing a local by reference. Which I actually don't want to do unless I could state as part of a lifetime thing. Now let's see. The function F says that the constraint is that the function will last, the potential closure of F will last as long as stuff coming in from the outside. But that would have been a lie, wouldn't it? Because it's actually a local value. I'm not actually passing F in by reference. Because I mean, I agree it has to be moved in because the iterator should own the function object. I want it to own the function object. If you construct a lambda, I don't want you to take the object that produces. Actually, it could be. What if it were a reference? So let me think about this. If it is a reference, I'm effectively saying, okay, so if I do a move of this thing inside, the closure itself is not just a function pointer, it may contain state. I'm only really constraining. Hold the phone. I'm only really constraining I'm only constraining the lifetime of F. F is coming in from the outside. It's being effectively passed in by value. If I were to remove this constraint and rebuild, it's going to tell me the parameter F may not live long enough. We need it to be the case that this thing is going to live at least as long as the iterator on which it is based. for the sake of anything that it itself may be containing, perhaps. And so that's why this has to live as long as the iterators live. At least as long as the iterators live, because if it goes away, or anything inside it goes away, the iterators, this operation can't work. It's holding on to iterators that we can't then force the values of through the function. So that's why this annotation has to exist. Now, as for this move operation, if I take this out, now we have a different problem. The closure may outlive its current function, but it borrows f, which is owned by the current function, which is exactly what I was saying. F here is coming in by value. We don't know what its type is. It's just something that adheres to this this trait interface. But the fact of the matter is it's still local to this function. I did not pass this by reference. And so because of that, effectively, everything here is a local value. And that means that I'm essentially returning a reference, because it's captured by reference, and it's capturing f and storing f inside the closure. It's storing a reference to f when I do it this way. That's why the move is required. There we go. That's the justification. And that means that what it's doing is it's now effectively copying f, whatever it happens to be, into the closure, and now the closure owns it. It's no longer owned by the function. I can't use it anywhere here. I mean, if I wanted to have more than one copy of it, I'd have to clone it. So what does that mean? Well, it's already, if I'm passing it in by value, it's already being cloned from the outside. So this really isn't hurting anybody on the outside of this. I'm again, not passing it by reference. That's actually an interesting question, though. There we go. There's an interesting question. Closures could capture small amounts of state, big amounts of state. It could capture crazy amounts of state. And if I'm passing it into this, I'm actually passing it in by value. I'm passing the closure in by value. And if it captures a pile of state, then so's this thing. But the point is that I made an implicit copy by coming in here. So from an efficiency point of view, what I kind of want to do is I want to say this function obeys this trait, right? But I actually want to pass it in by reference. And then I mean, the lifetime bounds still occur. Now, hang on, though. Here's the thing. Yeah, so that's interesting, right? Because this is local to the function, its lifetime is literally only local to this function. And so stating that the function, the closure that's passed in, has a longer lifetime doesn't really on the face of it have any meaning. It's not going to have lifetime past this function. It just won't. But something that it holds on to might. That's subtle. That's interesting. I think I've understood that part of it. Would never gotten nearly this far, this fast without Silenzy's help. By the way, very cool. Okay, let's run this and see what happens. This should now perform the zip following through to the zip width, following all the way through to my merge function, my merge zip width, as a daisy chain. Sadly, having to use the boxed in until we get the impl traits and traits. Yeah, I said that right. So, giving a great old big run here. Let's see if this explodes horribly. It has not. And in fact, take a look at this. Yeah, I should never do that again. So take a look at this. We have these two zips, for those who are just starting the stream, these two zips are coming from the standard zip operation. This is my zip operation that starts that starts from a zip, then passes through to a zip width that I've already written, hiding the iterator strategy it's using, which then goes one step further and calls merge zip width in order to do the operation. So zip width, merge zip width, And therefore, we have exactly the same behavior as a standard zip, but now we've daisy chained them, and there's all sorts of code reuse. And that's pretty awesome. Oh, that feels absolutely fantastic. Okay, and we have one more thing to do, though. At least one more thing to explore all of this fully. That's this dot operation. Now, if you require, if you remember, I rewrote my dot product operation here, so that used the standard zip and fold operations that Rust provides in order to solve this. And the way that that Rust has chosen to implement this is it doesn't have a zip width. It expects you to do a zip into tuples and then do a fold on the tuples. And I don't really have a beef with that, I guess, if it's like highly optimized, but it does require for me to create that intermediate struct. And if the compiler's not smart enough to see through that, then, I mean, I hope it would be, to be frank. But if it can't see through that, then it's creating this intermediate struct for no reason. And if it's a really big intermediate struct because I'm doing larger scale zipping, I guess zip only works for zipping two things together, I suppose. But if there were a zip 10 that zip 10 items together, or if the individual pieces were large and somehow the compiler couldn't see through it, I don't know if I like that. So let's fix this. Let's go back to the way that we were doing it before. So instead of zipping the two sides of the vectors into a tuple, because the only thing we're going to do with that is then add them together. We're going to pull it right back out of the tuple and add them together, and then, multiply them together, and then add it to an accumulator. Let's use mine. So we're going to do it mine where the zip width can be used instead of the zip. So we're going to do zip width, and we're going to say zip with v. And we're going to say the combining function for this is actually going to be xy. I guess the downside of this is I'm technically using two tuples instead of one, but whatever. Hopefully the compiler can see that through that too. So x and y yields x times y. And then that is then going to do a fold. And we're again going to start at R0. And then this is going to be slightly cleaner. It's going to be A and the summed value V. And that's going to produce A plus V. And I think, oops, sorry, that should be A comma V. Something like that. Now if we get rid of this, and it is now complaining. Well, wouldn't you? Look at that. So no method named zipwidth is found for parameter t's in the current scope. Really? Oh, because it's my zipwidth, because that's what I call it here. Ba-ding! Oh! All right. And there we go, 677, the correct dot product for that. Yeah, I guess the downside is that I do two separate closures, which boil down to function pointers because they don't capture anything. But I still make two function calls to the support functions, and I like the idea of using a zip width because that means I don't have the intermediate structure problem where the combined zipping is not a complicated structure. I don't have to pair it that way. Just another way to do it. This is the way I would do it in the Haskell version of the code. So, that's pretty cool. I don't know where to go from here. Yeah, so I'm gonna start getting rid of the broken code here. Not broken code, the code I don't need anymore because I'm daisy chaining these. Now again, the other version of this, for those who were not in the stream when I split off, sort of self-forked this, get rid of all of that because I don't need that either. That's pretty clean. I'm liking this a lot. So there is the zip width function, merge zip width function, that I started this whole thing off to find out about. Can I write a version of zip or zip width that I can use to do the searching part of the Advent 2020 first puzzle for the sum to n, and the merge part of merge sort, and obviously dot product and a couple other things as a higher order function? And the answer to that is yes. And daisy chain them together to boot. I think I have essentially solved the stream as far as I'm likely to go. Now, all of that having been said, I guess the next possible thing that I could do with this concept is a couple of things I'd like to do. I'd actually kind of like to benchmark a few of these things and try to do that in a way that's semi-friendly to startup conditions, I guess. Like, the biggest problem is going to take some work, so I may have to do some of this offline. But what I want to do is I want to have the data sets quite a lot more massive. And specifically, actually, the one I wouldn't mind testing would be the sums to n thing. Because I can just generate a pile of these things, random values, and do a hard search on it for the sake of the problem I'm after. Some conditions on that would be both, all of the implementations would have to do the kind of solution where I have a collection and a sorted collection. It'll have to take an unsorted collection, sort it, and do its reverse, rather than walk backward through the iterators, which I know would save me a copy. But what that means is that I kind of want to make sure that the setup for this, where I have the generated sorted and I have the. Do I want to time the allocations that this would... I don't really. That's not really my thing. Because the merge is a little too easy to test. Well, the merge isn't bad. Merge requires them to be pre-sorted in the first place, which means I can set those sets up without having to do the sort as part of the operation. I don't have to generate a second item that contains all of the elements. I'll have to think about how I want to test this. Benchmarking, just out of curiosity. I'm not really a kind of a language shootout kind of guy. I do respect the fact that Rust is trying to delve into the area of zero cost abstractions. I think that with a few enhancements, it would be my C++ replacement. It's getting awfully close. I do some kind of nice type wizardry in C++ that I like that are a little harder or impossible to do in Rust just at the moment. And some of it may be due to the fact that C++ does a lot of duck typing and its generics. But I also have... not sure if it ever replaced my happy love affair I've had with Haskell for a while. Largely because it took me about 3/4 of a page of code to do what it took about 10 pages of code in Rust. Maybe because I'm not doing it in a particularly efficient Rust-esque way. That will improve over time. And there are a lot of abstractions in Haskell which aren't zero cost, which means getting performance out of it. Certainly not impossible. There's some cool stuff you can do there, but sometimes takes a little bit of effort. Right then. Enough language babbling. I don't know where to go from here. I think I'm kind of out of things to do specifically on this project, except for what I just mentioned about timing this for my own amusement. So, where do we go for the next project that I want to do? I think what I want to do
I think what I want to do is experiment with something one of my friends was talking about, which was experimenting with Dijkstra maps, and those are kind of fun. They're basically a way to lay out in a grid the desires of agents moving about in that grid to be able to move around the space in an intelligible fashion. I found that kind of a neat concept. And so what I might do then is I might come up with a problem or an exploration that I want to solve, a simple task that I want to solve using them, and then implement those in the various languages as well. Do I have any cleanup I want to do on any of these? Not really. I'm not intending on putting this into a library or anything. I don't think it's necessarily worth that. So rather than start something on stream right now, it is already 4:38. I'm going to give this some thought and try to figure out where I want to proceed. Because the next thing that I want to tackle, ultimately, I want to start dealing with stuff which is less about the generic side of this and more about writing something with exploring more of the traits that I need to know about in Rust and dealing more with lifetime issues. And this means starting to process sort of real-world data in a non-generic sense for the most part. Probably have a grid of characters or integers. Probably going to have some I/O in order to be able to deal with that side of things. I need to build up data structures that are interesting for my problem space, like trees of data or grids of data, whatever. I need to be able to explore that side of it, including the lifetime analysis stuff. So, yeah. I'm babbling because I really don't want to quit the stream. I've had so much fun just doing this problem and figuring out the issues. Learning a little bit more about the lifetime stuff. All right. I'm just babbling. So, thank you very much for all of you joining me on this stream. I will definitely be back. I may not be back this evening. We'll have to see how I feel about that. I think I want to go and read a lot of stuff, maybe play a game or two. Actually, I may end up just fobbing off onto a game after the stream because I do streams on that kind of stuff too. This has been fantastic. I don't have a specific schedule, so just watch for me popping up. If more people start popping into my channels, then maybe I'll start doing something on the regular. But once or twice a week, maybe more than that. This week has been packed. I will come back and share stuff with you. Either games or code, probably, most likely. It's been fantastic. Thank you so much for all of you coming by to my stream. This is Codeweaver Writes Code, and I'll see you in the next stream.